Good morning.
Good morning and welcome to our 2025 capstone presentations for our stages trainees. As we get started, I just have a couple of items. For those online, if you can confirm that you can hear me.
Yes, we can hear you.
Okay, thank you, Emily. And you can see the screen.
Yes.
Okay, thank you. And then for those in the room, there is coffee and tea and water in the back of the room. We also have some breakfast pastries and items outside of the room. If you need to use the restroom, you go towards the entrance and take a left, and they're down that hallway. So with that, our agenda for today is we're going to start with a welcome by Dr. Murgulet and myself with some information about the Stages program and what we have done over the last 3 years. Then we will go into our trainees' capstone presentations, starting with our AirAware group, who worked with the Coastal Watch Association on an air quality monitoring project. Our Rio RAIngers group that worked with the National Weather Service on a project predicting whether thunderstorms originating in the mountain range in Mexico will travel eastward and make it to the coastal bend. We'll have a short break, so everyone can stand up and move around a little bit. And then we'll come back, and it's our Bacteria group that worked with the Texas General Land Office on a project looking at bacteria and predictors in Corpus Christi Bay. Each group time we will have Q&A specific to that group, but we've also reserved some time after all 3 groups present for an open Q&A and discussion for any questions you have for anybody in the room, whether it's the Stages Executive Committee, the stakeholders, or the trainees themselves on their projects or their experiences. Then we have lunch at noon, and then this afternoon, a sustainability discussion. But our trainees, you don't have to worry about that. You're free to go after lunch. Okay, so with that, I will hand it over to Dr. Murgulet.
Okay. Thank you, Audrey. Good, right? You can hear me? Okay, so what is stages? And we do this every year with this when we meet and the students give their final presentation. So for some of you, this might be just a repetition. The excitement, the voice, the tone might change on how we present it. So maybe pay attention still. It stands our Stages program, of course, which is a National Science Foundation Research Traineeship program, stands for Stakeholder-Guided Environmental Science, STAGES. So later on, we'll also introduce our new certificate, which is also Stages, but it stands for something a little different. Okay, so just keep in mind that the differences. And when we get there, we'll mention why we kind of changed the name. But it is, like I said, funded through NSF, supports interdisciplinary graduate training, and prepares students for a wide range of STEM careers. Our program brings together coastal and marine sciences, environmental data science, and applied big data science, including artificial intelligence, machine learning methods, all to co-develop with regional stakeholders this research ideas and the outcomes and outputs that are tailored towards their needs. So that stakeholder partnership is what makes Stages unique in Texas. In addition to the big data science and machine learning AI, which, you know, I think the world is doing right now, we have this niche to where we bring it to the stakeholders. So for those who want to explore more, The stages, we have a YouTube channel and a website where we post accomplishments, and we have, I believe, stakeholder presentations presenting their interests, our student presentations. So please check that out and also share it. So this is what we had in the very beginning. We have to have an organizational chart, of course. We all report to someone, and we all need support from the institution. So starting from the university administration with the provost, with the executive vice president for research, the dean of College of Science, because the program is hosted by the College of Science, going to the team, the main team. I have been the PI and program director from the beginning, but nothing could have been done by just by one person. Of course, we have the executive team that interact with the trainees, with the stakeholders. We have the faculty mentors, senior advisors like Dr. Montana has been an advisory committee, and we have external evaluation. So, and that is where our trainees know, or even our stakeholders receive that email from our external evaluator, from Audrey here, asking for feedback, because we propose something, because that's what we thought it's what we need, it's what's gonna be making this program great. Sorry, I shouldn't use my arms that much. But we just needed somebody from the outside to keep an eye on what we're doing and to give us the feedback that we need to improve year to year. And you'll see later when Audrey is presenting, for instance, the professional development seminars, how they evolve from year 1 to year 3. And not just that, all the other elements of the program have. So quickly, the stage's leadership, as you can see, the faculty, my colleagues, Dr. Epley, she joined us last year, but she has been a tremendous support and help us understand the other side of things that in sciences we are just, not necessarily paying attention or aware of, like how do you speak to a stakeholder and what can they share with you, and what should you expect, and what, in which form would you present your outcomes. But maybe at one point we'll have her speak a little bit. It reflects an interdisciplinary nature of the program, right? We have hydrogeology, political sciences, atmospheric sciences with Dr. Liu, marine biology with Dr. Pollack, AI or coastal systems with Dr. Tissot. So, and then I mentioned the external evaluation, and that's Scott Berg has been with us from the very beginning. Last but not least, Dr. Douglas, who has been the program coordinator. And I think this is also another element that makes this program very unique, in having a former CMSS PhD student, a scientist, come join us as program coordinator, made a huge difference, because she could always relate back to the experience as a graduate student here in that program, the needs, and as a matter of fact, we're just talking here with Dr. Tissot and herself, that when we're putting together the proposal, I would go back to her and ask her questions about her experiences and what was shared with her, what are the needs of our graduate students that we're not quite, thinking about it or incorporating in our program. So it's really was a good, well, we're lucky. Let's just put it that way. We were lucky she was still around, and we convinced her to stay with us. So a team-based approach, and is one of the reasons the program has been really successful, we believe. So at this time, I will hand it to Dr. Douglas to talk about what we.
Was it still here?
Still me?
Yeah.
Oh, okay. Oh, right. Oh, yeah, the proposed to do, not what we accomplished. Okay, so you just want to brag about what we did. Okay, so what we promised NSF in our proposal, our main goal was to create a new model for graduate training that responds directly to the needs of coastal communities while equipping students with advanced data and AI skills, among others. So it started with challenges, right? Not problems, but challenges is what we're using more and more these days, because that's an opportunity to do something, right? To grow, to improve. So we looked at what we are dealing with in the coastal environments, right? It's a lot of it's growing issues, degrading water quality, which turns into impact that impacts not only on human health, but marine life, local economies, and communities' health. These challenges, of course, like, we said water, then we said ecosystem health, then we said economy, right? It's all interconnected. So trying to understand those problems and approach them in a way that we can try to solve them without missing on other aspects. It requires interdisciplinarity, transdisciplinarity, and this is what led us to, these groups that the students have, joined in, that they are looking at the problem from a different perspective. They bring in their own knowledge and they are mentoring and educating and teaching the others in their groups. So another aspect of this program is also not keeping the research findings and what we do internally, right? Like we tend to just publish and stay confined within the academic circles. We need to reach and resonate with those who are most affected, right? Including the community, the stakeholders, policymakers. So our goal is to answer the questions that matter most to those groups. So including, what does climate change mean for local fishermen, right? What does water quality impact how does water quality impact the health of a community? So engaging in a meaningful dialogue between us and the communities and the stakeholders, we hope that we provide actionable outcomes. So what the stages do addresses all three challenges that are kind of what representation and also diversity in the environment and in data science was in the very beginning. Engagement with community, communication with stakeholders and policymakers, understanding this interconnected and critical challenges facing coastal areas. So we try to address all three challenges to create a new generation of diverse environmental scientists in coastal and marine system science, prepared to conduct big data analysis and visualization, and to use AI and machine learning techniques through team research co-developed with regional stakeholders. So the goals: to prepare students for leadership in interdisciplinary team science, strengthen communication and stakeholder collaboration skills, build a regional network focused on resiliency and data-driven environmental management, and develop a scalable, sustainable graduate educational model. So every activity that we did was driven by these objectives. And we have today a group presenting on bacteria with one of the group members, Muhammad, who keeps on saying, I'm talking bacteria. He's a geophysicist. And now we're talking about potentially biogeophysics. So that is actually a great conversation to have. So I believe I will skip this, but this is pretty much what the program is and what showcases and what we accomplished is Audrey is going to go over, but it is a series of courses that introduces them to team building and interdisciplinarity, to developing the research questions with the stakeholders during the summer or May workshop, to working and collecting data sets, cleaning them, and starting data analysis during the summer data updates into the environmental forecasting in fall, where they have worked and completed their capstone projects alongside other students that are taking the same classes. So with that, I'm gonna give it to you, Audrey.
So, I'm talking about what we've done because this has been my job, how we've progressed through the last 3 years from that initial proposal that I was given and read, and that was the roadmap. But then through evaluation and feedback from the trainees, from faculty, from the stakeholders, we've made adjustments to better suit the needs of all parties involved. One of the activities in the field trip and one of the adjustments that the Stages program made is in the Coastal and Marine Systems course, we introduced a field trip, Headwaters to the Ocean, or H2O. Thank you, Dr. Montagna, for coming up with that. And the purpose of the trip was to, within the Stages program, to foster team building amongst our trainees, but within the course, to encourage that transdisciplinary research and thinking. So we work in coastal and marine systems, but those are shaped and formed by inland processes. So we have river systems flowing to our estuaries, but where is that water coming from? We get rain for here. In Texas, we get rain generally up in the hill country. That feeds our aquifers, that feeds our streams. So understanding those inland processes helps better inform our understanding of the nutrient dynamics, the bacteria loading, other components that contribute to our abiotic and biotic systems in our coastal and marine areas. So initially, it was proposed that we would do the Nueces River Basin. So in year one, we went up and started with a tour at Devil's Sinkhole, which is a fascinating location. They do tours, so you can call ahead and schedule that. It is a restricted area, so can't get in without the tour. But we started there. It's a sinkhole, so it's cave formation that the ceiling structure collapsed. And from there, started discussing, so this is where the rain happens. It infiltrates into the groundwater, starts moving towards the river systems. We then proceeded to the Upper Nueces River, which it was a fairly dry year. And so in the Upper Nueces River, we'd reach a proposed sampling location and it would be wet. We'd go to the next one, it would be dry. So it demonstrates that there's not always an obvious surface connection between those upper rivers and the downstream river and the estuaries, which our students were not aware of. And so seeing that in person was quite interesting. As we progressed down, there were also areas where you could see the groundwater actually coming out of the bank. So you could see that bank discharge. But in year two, ultimately, we wound up shifting away from the Nueces River Basin to the Guadalupe, because Nueces, that's a long distance to drive in 3 days. And there's also accessibility issues because it's predominantly private land. So getting access, notice that whole middle area we couldn't get to. So we had a student that participated in the Texas Water Safari 1 year, so we were aware that we had a good system just a little bit further north that had those groundwater surface water connections even more visible at Spring Lake, but also had ready access points. So either it was public access to start with, or it was private property owners that were open to allowing us in. And it was a much shorter distance to drive. So instead of an hour potentially between sites, it was 15-20 minutes usually. So for cohorts 2 and 3, we shifted. There were still tours and stakeholder engagement was able to be brought in. So we went to the Canyon Lake Gorge and Spring Lake. We got to engage with I'm forgetting what it stands for, but GVRA, I think it's Guadalupe Blanco River Authority. And at Spring Lake with the Meadow Center and the Texas Stream Team. And then as we move down to the bays, the San Antonio Bay Partnership met with us and discussed their needs and their system. We also got to engage with private property owners along the way and discuss what they've observed over the last 20, 30 years that they've lived there. So it's one of the highlights of the program. It was adjusted over time based off of the feedback from trainees, and it will continue to be adjusted. Right now, we're looking to bring in even more stakeholders into meeting with the students and shaping the trip. Additionally,
Do you want to say anything about the other aspects of the field trip, including geophysics, the air quality, and the cross training?
so the cross training comes in where we proposed a certain set of sampling of samples to be collected, and then we invited the trainees to build upon that based off of their specialties. So we had geophysicists on the trip, and they did geophysics at the sites along the way. We had atmospheric scientists, and they had a portable air quality monitor that we put on the windshield of the vehicles and was recording continuously while we were driving. Early on, we had a student do biological survey at each site. So she was taking her net and going through and seeing, what was collected. Sorry, I'm not as familiar with that one. We did alkalinity and groundwater tracing elements. So, and the students were encouraged to be part of each type of data collection. Actually, in year 2, we had a student that was going to be collecting, I think it was bacteria sample, but she wasn't sure about her field method in collecting it. So she was testing her field method along the trip and refining it as we went. So there were students that were helping her with that. So everybody got experience or got to see at least a little bit what others do and discuss how it interrelates or informs each other's disciplines. And then we also have a paper about our year 1 field trip, the lessons that we've learned, that we learned on that trip, what worked, what didn't, what we proposed to improve. And as soon as I finish going through the proof, it'll be ready for publication next week, hopefully, fingers crossed. But that will be in the Texas Water Journal. The next big component is the stakeholder and community partner engagement. In year 1, this started as just a 2-day workshop. The first day, the stakeholders came, presented their needs, their ideas, and then we had a very short, ultimately, meeting with the trainees that afternoon. And then the next day, we broke out to discuss the projects of interest. The general feedback was it wasn't enough time to fully think about and assess the projects and engage with the stakeholders. So the following year, we actually, instead of a 2-day workshop, did a series of stakeholder mini workshops featuring 1 or 2 stakeholders that came and presented in more of a seminar format. And there was a lot more back and forth at that point in time. And these mini workshops occurred from March, April, and then we did a 1-day workshop in May where we invited everybody to come in. And our trainees then had time to assess all of the projects and decide which ones they wanted to focus on. And they presented at the 1-day workshop back to the stakeholders with their project proposals. This is what they proposed to do, and that led to breakout sessions in the afternoon to dive into each project in more detail with the prospective stakeholders. General feedback on that was that worked much better. So that was the same model that we applied this year also. and what we would recommend going forward for this type of co-development of research. Our stakeholders over the 3 years that have been able to find time to work with us have included government agencies like the National Weather Service, the General Land Office, NOAA Fisheries, Southeast Regional Office, as well as local nonprofits and grassroots organizations like the Texas Bends, the CB, start over, the Coastal Bend Bays and Estuaries Program, the Coastal Watch Association, Sierra Club, the Meadows Center. And actually this year, one of our trainees brought in a stakeholder group that she has worked with in her hometown, Friends of the Pecos River. And then also a little bit with industry with the Port of Corpus Christi. So along the way, we've also done professional development seminars. In year 1, these started as monthly seminars because we were, I think, hyper aware of how much time we were asking from our trainees. And we focused on science communication, we had an alumni panel, resume and CV workshop, and collaboration and teamwork. However, the general feedback that we got was that there wasn't enough professional development, and with monthly seminars, there's not enough time to do that. Also, in meeting and speaking with other program coordinators throughout other NRTs nationwide, we decided it became a very common theme that you just kind of have to say, this is the way it's going to be. And almost all the NRTs do weekly seminars for professional development and other skills development. So year 2, we rolled out weekly seminars and expanded topics. We brought in an expert on team science and project management. She also focused or did a session on communication within your team and communication with stakeholders and external collaborators. We discussed communication styles and how everybody's style is different. You need to have conversations up front about how your group is going to communicate. So are you going to use text? Are you going to use email? What format is everybody going to agree to? Science communication, for this, we had decided that our students needed to present more. So starting in June, once a month, they gave group presentations on their projects. So they gave project updates. And then they also gave once a term presentations on their individual research. So we had Dr. Montano came in and did experimental design, and another one on peer review and publishing. We had faculty come and give presentations on their research and how it is ultimately stakeholder driven also. And then our alumni panel. Year 3 shaped up fairly similarly, except where we positioned some of the seminars shifted. And then also with the addition of Dr. Epley Sanders, there was a focus on communication, not just to scientists, but to a broader audience. I think as she puts it, how would you explain what you do to your grandmother? That's right. We've also encouraged outreach to elementary school students. So how would you explain what you do to a 4th grader? We brought back more career-focused seminars because that was feedback from our trainees that they really wanted assistance on applying for jobs, on resume workshops. And one of our recent alumni who has been really effective with LinkedIn did a seminar on leveraging LinkedIn with his trainees. And this year, instead of the alumni panel, we did a career panel where we actually reached out to our stakeholders and asked them to come and talk about their career paths and what their recommendations are and what the current job market is. I believe I handed it back to you here, but Another focus of the STAGES program has been ethical and applied AI in environmental and coastal science. With this, we have focused on both course creation and development. So we created a new course, the Big Data Blitz. It's offered in summer, which is not a common occurrence here at the university, but the focus there is that for the STAGES trainees, they come out of the stakeholder workshop with their topics, and they spend the summer identifying and ingesting and pre-processing their data sets, while continuing the back and forth with their stakeholders about any potential issues they're finding and how best to resolve it, and further refining the research questions and objectives. They then go into environmental forecasting in fall, which was an existing course. That's where they learn about the AI and machine learning techniques that they apply to their projects. We also have become aware of different supplemental training modules that we have built into the courses or have strongly encouraged our trainees to pursue. So the Texas A&M University High Performance Research Computing Center has micro-credentials focused on Python and R, as well as several modules related to different types of AI and machine learning. And so in the Big Data Blitz, part of their assignments is to complete several of those micro-credentials. And then right now, the university for students, staff, and faculty are offering Coursera certificates, which focus on AI, but there's also some related to project management and stakeholder engagement. So we're encouraging the students there. But really, again, it's ethical and applied AI, so it's real data and real issues. One of our stakeholders pointed out in a survey that it's environmental data and it's messy. And so the students are learning that firsthand with these projects and learning how to troubleshoot those issues. So over the course of the 3 years in STAGES, we have had 25 trainees from 4 programs, and they've worked on 8 different projects. Those projects have been working with 5 different stakeholder groups ultimately. And we're very proud of our trainees. We've had 11 of them graduate so far. And they have, all 11 graduates have had 100% job placement or continued on to a PhD program. So there's a handout that was available in the back of the room if you didn't get it, that shows or lists what jobs they have gone on to, but some of them are data analysts, meteorologists. Some of them were hired by stakeholders that have worked with the STAGES programs. And some of them, a couple of them have said that they're pretty sure one of the major reasons they got the job ultimately was because of their experience in this program. So in spring 2025, we launched the STAGES Graduate Certificate. Again, this is a certificate. It's different from the NRT program. So we shifted the name slightly for what STAGES stands for. But it offers foundational training in applied analytics and stakeholder-driven research. Applied analytics, I do want to make sure you understand, does include the AI and machine learning aspect, as well as more traditional statistical methods. It includes 12 credit hours of coursework plus a 3-credit stakeholder project. And the certificate should be 100% aligned with the thesis and dissertation. So it is encouraging our students to bring a stakeholder into their thesis and dissertation research. Whether that ultimately is as a committee member or as a collaborator is up to them, their advisor and their committee. But that is one of the ultimate goals here is, again, that society-targeted or society-driven research. We also introduced the Patrick and Julie Nye Scholarship that supports one student annually that is pursuing the certificate, and it's a major step towards sustaining the program long-term. but we still need support. And for the students and both institutionally and broader to sustain this certificate program. So with this, I'm going to hand it back to Dr.
A little bit over here, but we do have, I think, enough time and that we accounted for. So this is what we will be focusing more on this afternoon session with hopefully the upper administration. But as Dr. Douglas mentioned here, we achieved major milestones, not only in graduating the students and job placement, and publication, field programs, AI-enabled field course, because the Big Data Blitz is a new course. The Coastal Marine Systems has incorporated now the field trip, which we're still working with to make sure it is meeting the needs of the students that are taking the course. We have a momentum here, and we're entering this critical phase for sustainability. This kind of grant, it is not a renewable grant. Okay, there are many STEM educational grants that universities apply for and get that can be renewed. They're mainly to pay a scholarship to the students to make sure they're getting support to do their research and maybe do some professional development, and they can always be renewed. This is a one-time deal, and you have to prove that you have been successful and that you do get support to institutionalize elements that you think they worked, right? And of course, we proposed so much more when we proposed, okay? What we do now is probably a little less than 3/4 of what we were gonna ask the students to do. I'm sorry, guys, I know you have worked really hard, and we didn't say how proud we are, but we did say it a little bit, but we know how much you had to work to be part of this program. Because you had to keep up with your own research while doing this training and engaging with the stakeholders. But we do hope that the tools you learn have or are helping you with your own research, so hopefully progress faster. If this was a little delayed, it's delaying you a little bit in your progress. So to sustain the program beyond the NSF award, we need support in 3 areas: the institutionalizing key program elements like the stakeholder workshops and faculty leadership and big data science, or like AI and machine learning based courses. The reality is that for the past year or two, we have been relying on our postdocs or program coordinator to take on some of these courses, and Dr. Narimani has been teaching the environmental forecasting after Dr. Tissot couldn't do it. This was the 2nd year. She is very good at this, but she also has her own career that she needs to focus. To the Big Data Blitz, the same. And so Dr. Douglas is taking on the Coastal Marine System Science, which I think is a good idea because of her interdisciplinary mindset. But we do need support to cover faculty lines for this, because what the stakeholder engagement is great, and this is our unique niche here. But the machine learning AI, everybody's doing it, and if we're not investing in this, we're going to be very much behind and not keeping up with the rest of the world. So dedicating teaching capacity to these courses is essential. A full-time, part-time PhD level program coordinator that could engage with the PhD programs and graduate programs, to where graduate students feel like they can go and talk to and get guidance. We as faculty advisors do that as well, but we are very busy, and sometimes students find it a lot easier to talk to somebody else than their advisor, or they just need a little bit more time for the administrative side of things, not for their research necessarily. And so to take care of all of this different components, like the workshop, the engagement with stakeholder, it's not an easy one to do because everybody's busy. Just going after finding time to work, who will work, who can do what, is extremely important. So that program coordinator, we need that program coordinator that also has the vision, right? That's why we say the PhD level program coordinator for logistics, partnerships, student support, to keep the program functioning. These investments will hopefully maintain the strong graduate pipeline we build and stakeholder engagement. So hopefully we will get there. So now we're transitioning to our cohort 3 capstone presentations. But before that, I think we did not do the introductions, so we do need to do the introductions. We have time, so don't stress out. You'll get the time you need to do your presentation, okay? We have the break, and then we have time at the end. So if we're running a little bit later, it's gonna be fine, okay? So we'll go around the room quickly, and then also would like to introduce our guests that are online, because we're not seeing that. So start with the online people. Okay, we can do that. Can Emily, would you introduce yourself since you're first that I see?
Yes. Hi, everyone. I'm Emily McGee. I'm a master's student and I'm part of the Stages Cohort 3. I'm in the BacteriAI Group. I studied dolphin acoustics under Dr. Dara Orbach, and I'm graduating this semester.
Madison?
Hi everyone, my name is Madison Reba. I was a master's student in the cohort 1 of Stages. I have a master's in mathematics and I'm currently a data analyst for the Railroad Commission in Texas.
And Madison was part of our program, one of our trainees, and they did an amazing job.
This is being wonky.
There you go. Okay.
Lucy?
Hi, everyone. My name is Lucy Flores. I'm the project manager for Texas Beach Watch, and I'm excited to hear about the students' work on BacteriAI.
B?
Hi, I'm B. DeBona. I was in cohort 1 and cohort 2. I did my PhD at A&M Corpus. I graduated this past May, and now I'm a postdoc at UTMSI.
Melissa? Okay, Angel?
Hey there, everyone, if you can hear me. My name is Angel Enriquez. I'm a meteorologist here at the National Weather Service office. I'm just excited to see some of the upcoming work being presented from Sophia and Jericho, so looking forward to it.
And Dean Michaela?
Yeah, hi, good morning. Rob McCall, Dean of the College of Science. I'm really excited to learn more about this NRT Stages program. My apologies for not being there in person, but I'll try to, I'm going to be there this afternoon and hope to meet each of you personally.
Thank you. Thank you. And Jennifer, can you bring up the chat and read Melissa?
Yeah, so Melissa Smuck is from NOAA Global Ocean Monitoring and Observing, and their PhD was from here at TAMUCC. Thank you, Melissa.
Everybody. That's everybody online, I believe.
We're moving to.
Oh, okay. I'm Dr. Jennifer Lee Sanders. I'm a professor of political science here at the university, and I've been very fortunate to be part of this interdisciplinary team. And later, when we have informal Q&A, you'll hear me gush about our students a lot. And so I'm happy to be here and also happy to answer any questions later.
Hi, I'm Jenny Pollock. I'm the chair for coastal conservation and restoration here at the Hart Research Institute. And I've been involved with the project since the writing days with Dorina and the rest of the team.
I'm Paul Montagna. I'm one of the professors.
And our mentor, and yeah, Dr. Montana is not bragging about anything, but an essential part of CMSS program, and for us as faculty, a mentor. So.
Morning, I'm Danny Coffey. I'm an assistant professor in the Department of Life Sciences here at TAMUCC and the faculty advisor for Jasmine Nice.
I'm Peyton Campbell. I'm the science coordinator with Coastal Watch Association, which is a local nonprofit, and I work with universities and other nonprofits.
Hi, I'm Max Portman. I'm a PhD student with Dr. Ed Profit. We do like mangrove ecology, and then I'm new to the Stages program as of this semester.
So he is part of the certificate program. Hasn't been part of the training per se, but has been attending seminars and
In the first class.
engaging with the cohort this semester. Okay.
What am I supposed to say?
Just introduce quickly, because you're gonna get a chance to say
Yes.
more about you, but yourself.
I'm Sophia Mahalik. I'm a marine biology master's student. I'm a current member of the Rio RAIngers.
Hey, everybody. I'm Jerica Rosili. I am a part of the Rio RAIngers Group as well for Cohort 3, and I am a CMSS master's student.
Hi, everybody. I'm Jazz. I am a second year PhD student, and I am part of the Error Aware team. So you'll hear a little bit more about us in just a few moments.
And I'm Delaney. I'm a master's student in the CMSS program, and you'll hear a lot more about us in a couple seconds. So I'll pass it off to Mohammed.
Okay, this is Mohammed. I'm a PhD student working with Dr. Dorina Murgulet. I'm in BacteriAI Group as well.
I'm Cody Lopez, another PhD student. I also work with Dr. Dorina Murgulet in this group, Center for Water Supply Studies, and I'm also in the BacteriAI Group.
Hello, I'm Jane. I'm a doctoral candidate. I'm working with Dr. Sadowski.
Louder.
I'm working with Dr. Sadowski and Dr. Belsaba, and I'm working with also the Bacterial project.
Nick Carr, I'm the Science and Operations Officer at National Weather Service-Corpus Christi. I work with Sophia and Jerica on their project. I'm excited to hear about all the other projects as well.
Quincy, and I'm a first year PhD student. Last year I was a part of Cohort 2 as a trainee, and this year I returned to Cohort 3 as one of the student mentors.
Juntao Liu, part of executive committee as a professor in atmospheric science, and I help in the coding foundations for the student.
You.
Beijing Xie, I'm a professor in the M6 science program in College of Science, Paris. So one of the students involved in the stage program. Thank you.
Heavily. Okay, back to Narimani.
Hello, everyone. I'm Roya Naimani. I'm a postdoc. I'm working with Dr. Murgulet, and I'm the one who's teaching environmental forecasting. And nice to see you here.
I'm Philip Tissot. I'm at the Conrad Blucher Institute, Chair for Coastal Artificial Intelligence, co-PI on this grant. And I love this grant because working with stakeholders and pushing research is in the DNA of this institution, 80s, 90s, etc. And Dr. Murgulet and Dr. Douglas and the team has really pushed it to another level, improving year after year. And I think this is a great foundation to keep it something that's needed. So I see a lot of future, hopefully, in continuing this.
Hi, everyone. My name is Michaela. I am a PhD candidate in the marine biology program. I was a student in Cohort 1 working on the Seagrass project, and I am now a peer mentor for Cohort 3.
Thank you, everybody.
Thank you. With that, I will move into transition into our capstone presentations. Again, we'll start with Delaney and Jasmine with They're Aware.
And we do have a packet, a handout there with their summaries, all the three project summaries. We didn't have a lot of time to spend on this, but the attempt was to have it kind of translated science for any reader. So please pick up one.
Good morning, everyone. We're going to jump right on into it and how we spent our last 6 months. Our project is called AirAware, and we were predicting coastal air quality with machine learning. But before we get too far into this, we want to give some quick acknowledgements. Of course, to the Stages program for allowing us to even have this opportunity to discuss with stakeholders about their issues and also how they would expect science to be used in their projects. And the Coastal Watch Association, we actually had a wonderful time collaborating with them, using their data and so forth. And of course, Corpus Christi for even allowing this to happen. My name is Delaney Peters. I'm a second-year master's student in the CMSS program under Dr. Fay. My background is in atmospheric science, actually from Corpus Christi. And then my thesis focus is on planetary boundary layer height detection using GNSS radio occultation, which basically just means I use GPS satellites to look at the lowest portion of the atmosphere. And it's super important for weather and climate forecasting and also air quality modeling. And with that, I will let Jasmine introduce herself.
Hello, I am not an atmospheric scientist. I am actually a marine scientist. I am a second-year PhD student in the MARG program. My advisor is Dr. Daniel Coffey. I actually have a background in fisheries where I got a degree through the University of Alaska Fairbanks, and also marine science where I got my BS from the University of New England. And my dissertation focuses on the movement, trophic ecology, and contaminant exposures of different fish in our local bays and estuaries, mainly southern flounder and sharks and rays. So let's jump right into it. And I want to start with a little bit of a background on our project and this area. So firstly, Corpus Christi is a major oil and petroleum refining area on the Texas coast. And it is also a huge shipping hub here on the South Texas coast. Now, because of this, we do have elevated regional air pollution. And because of the wind that is in South Texas here in Corpus Christi, we are one of the windiest cities in the country. All of that wind will actually bring those pollutants into our inland coastal communities. So currently, a lot of the air quality monitoring is actually passive, which means that all of the residents don't actually find out about these poor air quality days until the days after these events have already occurred. Which means that as new permits come into our area and more things are coming into Corpus Christi, we just built a huge new bridge, which brings in lots of new ships and larger ships. It's going to further impact the regional health and especially for our coastal communities. So that brings in kind of the big portion of why we're doing this project is to develop real-time monitoring to give our community a better idea of how good the air quality is going to be and have a little bit more of a proactive air quality management in our local community. So when I'm talking about air pollutants, you may be wondering what exactly does that mean? And there's lots of different things that fall underneath of this category. I'm just going to list a few off for you. So those include particulate matter, which is both fine and coarse particulate matter. So that's 2.5 and 10. We also have ozone, which is going to be designated as O3 throughout this presentation. Nitrogen dioxide, sulfur dioxide, carbon monoxide, BTEX, which are different types of benzene, toluene, ethylbenzene, and xylene, as well as black carbon and volatile organic compounds. Now, all of these things probably sound a little bit scary, but we do have a lot of monitoring through the EPA and also Coastal Watch Association for those that are bolded here on the screen. Now, as it comes for sources and where these things actually come from, we're talking about engines, different vehicles, petroleum refining factories, as well as volcanoes and different types of storage for different gasoline and petroleum. So that's where all these sources are coming from. And as we all know, we have a lot of those refineries and sources here on the South Texas coast. Now, for health impacts, this does impact a lot of people with asthma. It causes negative impacts to the heart and lung, respiratory issues, sore throat, all of these difficult breathings, and even carcinogens. So when we look at black carbon, we're talking about carcinogens and certain types of BTEX as well. So this is obviously something that all of us want to be aware of as members of our community, right? But for the purpose of this project, we are going to focus specifically on PM 2.5 and ozone. So that is something that we came together together with our stakeholder and chatted about what would be most important for our local community. So PM 2.5, just for scale here, is anything that is smaller than 2.5 microns. So if we see the human hair there is about 50 to 70 microns, these are really small particles that we're talking about. And ozone is going to be a mixture of different components that are heated up by the sun and cause smog, which typically can cause a lot of respiratory issues. Now, I'm going to pass it back over to Delaney to talk a little bit more about our stakeholder and some of the models that we based all of our work off of.
Perfect, thank you. Just to give you guys kind of a background on what the Coastal Watch Association does. They're a nonprofit organization based out of Ingleside on the Bay. They promote environmental health and safety as well as public awareness throughout scientific research and education for the public. They partner with other academic institutions as well as Corpus Christi, and they monitor air quality across San Patricio, Aransas, and Nueces counties, among other things, including their water quality, but that's outside of the scope of this. So how are we currently monitoring or calculating what all of these pollutants are? So the EPA does have a sort of framework for forecasting, but it's a little bit complicated. So for particulate matter specifically, they find the highest and the lowest values within that hour, and then they take the average. They also figure out how much the particulate matter changed within that current hour, figure out how quickly it's changing, and then they create a weight factor that tells us how much we actually trust the older data. This gives more importance to recent hours rather than older hours because your particulate matter is not going to change very much from the hour before, but from 12 hours prior, it's probably going to be a little bit different. They combine all of these things into a single estimate, and then they convert that to the air quality index. Excuse me. Sorry about that. And then for ozone, it's even more math intensive. They create two moving time windows. So they take the past 4 days of information and they also take the past 14 days of information. They fill in the missing data when possible using a 3-hour rolling average. But if there's more than 3 hours missing, they just disregard it and say it didn't have a number. So we're not going to predict it for you. They calculate the 8-hour average. Then they slice the long-term data into those 4-day increments and calculate the corresponding 8-hour average for each of those increments within the two-week time frame. They use partial least squares regression to model the relationship between that short-term window and the long-term window. And then they model that current estimate and change that to the air quality index, which is a bit out there, but they also don't take any outside environmental forecasting metrics. So what our research objectives were to develop a predictive model using AI and machine learning to forecast the air quality on the northern side of Corpus Christi Bay using environmental data as well as particulate matter and ozone data. And then the objective number 2, most important in my opinion, was to make sure that the public can use our data and understand where it's coming from. And with that, I will let Jazz talk about how we even decided to do this.
Okay, so I'm just going to walk through some of our overarching methods here. So we are going to begin with our data ingestion where we're actually getting all of our data from Coastal Watch Association, but we're also going to couple that with meteorological data from the NOAA ports stations, which are local, and we are able to then get that publicly accessible data. So we're going to pull all that in together and we'll be able to work with that data. The first thing that we have to do is what we call pre-processing. So this is when we're basically doing quality assurance, quality control checks on all of our data. We want to make sure that we are looking for any data that may be missing, sensor malfunctions, and through working with our stakeholders so closely, we were actually able to determine a few spikes within our PM that were actually due to spiders nesting in the sensors. So these are things that we have to kind of keep in mind and something that we were able to figure out with our stakeholder because we were working so closely. But we also needed to remove some co-location dates where these sensors were being either changed over or moved around to make sure that all of the data is going to be the same for each of those locations that we are looking at. Once we get all of that figured out, we're going to move into what we call data mining, which is when we're actually looking at patterns and different types of summary statistics of our data. And then we can start to manipulate our data a little bit. So one of the big things that we wanted to make sure to do, because it's relevant for the goals of the project, is to assign air quality indices to each of our readings, which are called EPA NAAQS, National Ambient Air Quality Standards is what that stands for. So what we'll do is we'll categorize all of our data into those NAAQS categories, which will allow us to then move on to the modeling component of the project, which is where we actually go into building our model. Now, as Delaney had mentioned, we want to implement this EPA Nowcast framework, but we want to add in those meteorological data so that we actually have an understanding of what potentially could be driving these pollutant dispersions. We'll train 2 different models, and we'll go into those details a little bit later, but we'll be working with random forest and cat boost models across a horizon window. So same thing as if you were to get a weather forecast for the week, we're going to do a similar thing where we're going to look across a week-long period. And then we'll come to the end where we'll actually evaluate this model performance and look at which features within the model are most important to those predictions. Now, getting into the data a little bit more specifically, the bulk of our data is coming from the Coastal Watch Association ground monitoring stations. So there's 8 different sites that record data every 2 minutes, and this is going to be in a CSV format that we can then compile all into one single format of CSV format. And the variables that we'll be looking at in this data set are going to be the PM 2.5, ozone, air temperature, and humidity. Now, to pair this with the meteorological data, we're going to take the NOAA port stations data. This records data every 6 minutes, which you may be wondering, how did we kind of aggregate this data in the same time period? So we actually ended up averaging over an hour-long period. So the mismatch of time periods doesn't really matter in this case. But we have 4 separate sites, which I'll show you in a little bit on a map. And the variables of interest here are going to be wind speed and direction, as well as temperature, dew point, and pressure. So these are the things that we'll be incorporating into our data set. Now, for our data mining, like I had mentioned previously, we go into looking at patterns of these 2 pollutants of interest, which is PM 2.5 and ozone. We're going to group our stations together based on geographic proximity, which I'll show you in just a moment. We'll also flag these PM 2.5 values that are above certain thresholds. This is actually how we were able to determine that there were sensor malfunctions or even some issues with a few of the sensors, and we could then remove that data so that our model was not being fed data that wasn't necessarily true. We'll then assign those NACS categories, as I had mentioned, and we will not be filling in any of these data gaps because we didn't want to introduce any bias into our data set, especially because our stakeholder was going to be using this data in a real-time monitoring. So we want to make sure that we're providing them with something that's realistic for the data that they will have. Now, looking at some of the pattern discovery, this is just a brief table showing the time ranges, the 2 pollutants, the minimum, maximum, and the mean of all of those at the 4 separate locations that we have. And there's just a few things that I want to mention that will become important as we are going into our data interpretation. So firstly, we want to note that Hillcrest only has about 6 months of data, whereas the other 3 sites have multiple years of data. So this is just something to keep in mind as we move through the project. For the PM mean, we actually see the highest PM values at Ingleside, but the maximum PMs was actually recorded, the highest amount of PM was recorded in Portland Gregory. So these are 2 sites that are really close in proximity to this industry lane, as we call it. And this is something just to keep in mind as we move forward. And lastly, for ozone, we actually see the highest ozone readings in Port Aransas, both for the mean and the maximum values. So again, this is something to keep in mind as we move into our data interpretation. Now, before we go into a little bit more here, I want to just first touch on the study area. So this is a map of all of our locations where we have ground monitoring stations from Coastal Watch Association. So those are color coded by 4 different colors, which correspond to the 4 different groups that we have. So starting on the right, which is our coastal environment, we have Port Aransas, which is in the orange square. We then move a little bit more inland to the blue circle, which is Ingleside. The green triangles are Portland Gregory, and then we have a hexagon there with a pink hexagon for our Hillcrest location. Now, all of the red dots there are our NOAA port stations. So we can see that some of them are within the 3-kilometer buffer period or buffer zone of those stations, specifically with Port Aransas and Ingleside. And that 3-kilometer buffer was used to just group these together because for EPA regulation standards, the neighborhood scale of air quality indices is actually 0.5 kilometers to 4 kilometers. So that 3-kilometer buffer period is just what we ended up using for visual purposes here and grouping together of our stations. Now, for our air quality indices, there is actually a roadmap here of the 6 different categories that you can actually categorize air quality as. So we have good all the way down to hazardous. Now, we originally wanted to model all 6 of these categories, but unfortunately, there's just not a whole lot of data, which is a good thing in those really bad air quality groups. So we actually grouped together those 4 bottom categories as bad, because as me and Delaney discussed, and as we discussed with Peyton, if anything's above moderate, as a person in this community, I would like to know about it. So we grouped those all together into a bad category. which looks something like this. So we have our two different pollutants here and our averaging times for the 3 different levels of those air quality indices. And you can see we have a lower and upper bound. Those are just the raw number readings for those groups and the AQI there on the right. Now, before I pass it over to Delaney to talk a little bit more about how we actually build our models and what we put into our models. Sorry, go ahead. Oh, I read it wrong. Oh, sorry. I just want to briefly talk about the 2 different modeling strategies that we use. So the first is going to be random forest models. This is, as the title kind of alludes to, an algorithm that is built off of decision trees. So that is pictured here on the right. And for each tree, they're actually going to look at a random subset of our data. So if we look at this figure here, we start with our data set at the top. We have then 3 different decision trees that come to a result. And based on that result, depending on if you're looking for a classification or if you're looking for more of a regression, there will either be a majority voting or an averaging occurring so that we get a final output there, which basically improves our accuracy and reduces errors within our data. Now, the other version of a model that we'll be using is called CatBoost, which is named categorical boosting. So this is also using a tree method, but this is called a boosted regression technique, which means that it is learning from each tree that is built before it. So for each tree, there's going to be some error associated with that result, which means that the next tree will learn from that error and eventually it will create a really nice improved prediction for us. So if we look at the figure here, we'll start with tree 1, and what it's trying to do just for this schematic is sort the dots into blue and orange dots. And it'll make a decision, and based on the error for what it was actually sorting, it will make another decision and another decision and so on. So it creates an ensemble of decision trees, which allows us to have a really accurate prediction at the end of our model. Now I'm going to pass it over to Delaney to talk a little bit about our specific model and the inputs that we put into it.
Great, thank you. So what did we put into these 2 different types of models? So we actually had 453 different inputs that we put in, except for Porter Ranges, who's technically missing humidity because the buoy doesn't have any humidity. But what were those things? So for our 2 variables, or our 2 variables of interest, particulate matter 2.5 and ozone, we took the hourly mean, maximum, and minimum, and then also the standard deviation, which is very similar to how the EPA predicts things. And then we also included the nowcast value from the EPA because that's something that they do predict, and that's something that we could use to make our model a little bit better based on forward proceedings. And then what meteorological inputs we do, we include the wind component, but we break it down into U and V. So a typical wind variable is going to be in 0 to 360 degrees, but for a model, it's kind of hard to understand what that means. So we break it down into its east and west and north and south components to make it a little bit easier for the model to understand the relationship for the wind direction. We take the hourly mean and standard deviation, and we also take the maximum and what the mean wind gust was for that hour. We include air temperature, pressure, dew point, and we calculate relative humidity, including the hourly means and standard deviations. And then we include the day of the week, day of the year, and the hour that the time was, or the hour that the measurement came from. And I'll get into that a little bit more here in a second. So how did we actually tune our models, and what did we do to make them a little bit better? We introduced time-lagged features. So we took the previous 24 hours worth of data and implemented it into our forecast. We did some tuning. So basically we took 30% of our training data, put it into our models, and let it decide what parameters were best for our model to be the best model moving forward. So for random forest, we tuned how many number of trees it created, how deep those trees can go, and then what the sample split was going to be when you put in for an input. The CatBoost was very similar. So how many times it was going to make a decision, how many decisions it was making. And then the learning rate, which just means how much information it's taking from the previous tree to learn and move forward and get better. We also included a time series split of our training and testing data. So basically this just means we trained our data on the oldest data, and then we incremented a little bit more data by little and allowed it to train on itself. And then we tested on the most recent data. We also implemented class weighting, which, as Jasmine alluded to, we don't have a ton of bad air quality to model on, which is great for the general public, but for a modeling standpoint, it is very unfortunate. So we implemented this to give more weight to the bad air quality when it's predicting and less to the good. We also did cross correlation, which removed any highly correlated predictors within our 453 inputs to reduce redundancy. And then finally, we added those temporal features. So we included the day of the week to encompass traffic influences, because as we mentioned earlier, ozone can come from engines and create more smog. So Monday through Friday, you're going to have more people driving. Saturday through Sunday, you're probably going to have less information. And then we did day of the year, because the wintertime tends to have a higher concentration of pollutants just because there's more people burning wood in their fireplace. The boundary layer is actually lower, so it keeps the concentration of pollutants closer to the ground, etc. And before we get into our results, I want to give us a little bit of a vocabulary background so that we understand what I'm discussing moving forward. So the F1 score is, and as Dr. Murgulet is pointing out, it's also listed on our terms of importance in the packet. So the F1 score is a balance of identifying the positive cases while avoiding the false alarms. Accuracy is just overall correctness. The macro F1 score gives a fair view across all classes. So basically it treats our small classes equally to our greater classes. We implemented the high key skill score, which quantifies how well the model performs just compared to random chance. The peer skill score is very similar, but it's not as influenced by class imbalance as the high key skill score. And with that, let's get into what we found. So, to kind of orient us here, we're going to go from the coast and work inland. So our first location is Port Aransas. The table on the bottom shows what our percentage of data was. So as you can see, we had really good air quality for particulate matter. Not a ton of data for the bad air quality. And we can see that in our per category F1 scores in that top figure up there. So green is good, yellow is moderate, and red is bad. As you can see, both models, the cat boost in the squares and random forest in the circles, do really well at predicting good air quality. This drops off when you talk about moderate, and then hardly ever predicts bad air quality. This is also easily seen in the overall macro F1 scores. So early on in the forecast, both models do relatively well, but as you go further on in the forecast, they kind of decrease in their accuracy. But this is very similar to a weather forecast. So you really trust your weather forecast 24 to 48 hours out, but once you start getting 5 to 6 to 7 days out, things can change within the model, so you don't necessarily give them as much weight. And then in the high key and peer skill scores at the bottom, we can see that these models are very similar in metrics when compared to chance, does really well early on and then kind of falls off later on in the prediction forecast. Now for Ingleside, we have a much greater spread of data. So our good quantified about 70%, but bad took up 5%, which I feel like is most important when it came to actually predicting the bad air quality, as you see in the top plot there. Both models do really well predicting good. Cat boost starts to kind of outperform random forest when it comes to moderate, and then it does extremely well or better than random forest when it comes to predicting bad air quality. And you can also see this trend in the macro F1 score, where the cat boost is above 65% accurate at 24 hours, and then kind of falls off to around 50% accurate once we get out to a week. Whereas random forest stays below 50% the entire time. And again, cat boost is outperforming when compared to random chance and the HSS and PSS scores on the bottom. Next, Portland Gregory. There's a little bit less of a spread, but moderate does take up a little bit more than our Port Aransas location. Both models do really well with the good. Cat boost kind of falls off when predicting good, but does significantly better when predicting moderate air quality. And then the random forest trails off to about 10% correct. We can see the same trend in the overall, where both are equally as important when predicting, but cat boost tends to overperform or outperform random forest. And again, you can see in the HSS and PSS where the scores themselves are a little bit lower, but we see cat boost still outperforming random forests. And for Hillcrest, I'd like to remind everybody we only had 6 months of data for this location, so there wasn't as much to train our models on. There was good air quality about 78% of the time, moderate 21%, and bad only 0.2%. I fully believe that this is because the data we had was in the spring and summer months, so there weren't necessarily many bad air qualities to begin with. Both models do really well at predicting good, as we see this general trend. CatBoost outperforms Random Forest in predicting moderate, specifically in the 24 and 36-hour time frame. And then neither one of them do really well with predicting bad air quality. But again, there wasn't really data for us to predict, so we're not going to do well. The CatBoost, we have that general trend of doing really well 24 to 48 and then decreasing moving on. But interestingly enough, the Random Forest kind of stays about the same throughout all forecast horizons. But when we look at the HSS and PSS scores, CatBoost does extremely well, or considering Random Forest does much better than the Random Forest, whereas the Random Forest looks like, even if you were just to say on a random day your air quality is going to be, say, 50 AQI, Random Forest doesn't do very better when thinking about random chance. CatBoost is similar when you get farther out, but it does better performing in those early forecast hours. And with that, I will let Jasmine talk about our ozone results.
Okay, so ozone. We're going to see very similar stories to what we did in PM, but the ozone results are also pretty interesting. So we'll begin again at the coast, starting at Port Aransas, and just orient everyone again. We have the F1 scores, macro F1, and then our HSS and PSS scores on the bottom across the forecast horizon. So for this specifically, we actually had about 5% was bad air quality days for our data inputs here. But again, we see that the good air quality days do really well across the entire forecast horizon, whereas the moderate and the bad don't do as well. We see here that the Random Forest actually is outperforming the CatBoost in those macro F1 scores across the entire horizon, which was pretty interesting. And we had thought maybe that had something to do with the amount of good air quality that we were able to train the model on. And you'll see a relatively similar trend across all of the ozone for the HSS and the PSS scores, but these are relatively low and they kind of jump all over the place. So that's just something to keep in mind. Now, moving to Ingleside, which was, again, one of our sites that had a lot of data. Again, we see that the good air quality for ozone across the entire forecast horizon is being predicted really well in those F1 scores. And our CatBoost does really well with the moderate in this site. So we actually have a pretty high F1 score across the entire forecast horizon for that. Whereas Random Forest for the moderate, and then both of the bad air quality days do not do as well across the forecast horizon. But here we see the flip in the macro F1 scores, where we have CatBoost outperforming Random Forest across that entire horizon. And we can see that again with the HSS and PSS scores. Those are higher than the Random Forest across that horizon. Now for our Portland-Gregory group, we did have about 93% of those good air quality days and 4% and 2% for moderate and bad respectively. But again, we see that the good air quality across the forecast horizon is very high, where our moderate and bad air quality is fairly low. And we have Random Forest and CatBoost performing relatively similar for the first 48 hours, but then we see Random Forest kind of maintains this consistent macro F1 score, whereas CatBoost kind of jumps around a little bit. And again, we have those pretty low HSS and PSS scores. And lastly, Hillcrest, which Delaney did mention in the PM results, that we only have about 6 months of data for this. And again, we see that the good air quality for this group was good across the entire forecast horizon, whereas the moderate and the bad did not do as well across the forecast horizon. And the macro F1 scores, again, kind of flip-flop back between Random Forest outperforming and then CatBoost outperforming, and the HSS and PSS scores are relatively similar. So I'm going to throw it back over to Delaney to talk about features of importance before we round out to the end of our presentation.
Great, thank you. So we put these 453 things into our model, but we wanted to understand what was actually driving what our model was using to make a prediction. So we did this for each model, for each location, for each variable. So it looks like a lot, but the main takeaway for particulate matter 2.5 is that the day of the year and what the nowcast value are what our model uses most often to determine what the current forecast should be. And then for ozone, again, for every location, every model, we see a very similar trend to the day of the year, but the hourly mean is more important than what the nowcast was, which tells me that making that forecast depends on the current hour rather than the previous hours. And with that, what do we take away from all of this? So machine learning methods can be used in a predictive capacity for air quality monitoring, specifically in the coastal bend of Texas. Cat Boost outperforms our random forest model. When you consider the class imbalances, we would rather predict bad air quality and it not actually be bad, rather than not predict bad at all, and you would never know that it's bad. Ingleside is a great case study because it has a lot of data. Its proximity to the shipping channel and refinery interactions give us a worse air quality to deal with when modeling. And other locations either don't have a lot of data or a significant distance away from the meteorological parameters that we were using. So this decreases our effectiveness in predictions. So our results actually do match trends from other coastal and industrial locations such as Japan and Ecuador. The sea breeze affects the pollutant dispersal, as we see in Port Aransas. And then the model limitations are actually that we think are driven by class imbalance because we have very few bad air quality events, which is great for the general public. But when you're trying to model these things, not having an example to model on is kind of tough. The uneven monitoring duration across sites, so less amount of data at Hillcrest makes it a little bit worse than Port Aransas. The meteorological parameters aren't necessarily directly where the monitoring is happening, so it may have shifted slightly. And then the sparse spatial coverage are also noted as other challenges in other studies. And with that, I'll let Jasmine talk about where we're going to go from here.
Okay, so some future directions to consider for this project is incorporating near real-time data to make active monitoring and warnings possible, which is something that we hope to do with our stakeholder in the future. Adding in meteorological parameters at the site where these pollutants are actually measured is a fantastic direction forward. As Delaney mentioned, not having the NOAA ports stations, really close proximity to the Coastal Watch Association may lead to some of these differences that we're seeing across our models. And lastly is adding in more stations, which can expand the coverage. And we do know that our stakeholder is looking to implement some new monitoring sites. And we want to just showcase this here, which is a social vulnerability index overlaid with where our stations are actually located in the area, which is a great way to look at the different types of groups and communities that could be supported through this project. So the social vulnerability index is actually a composite metric that is looking at disability, access to transportation, poverty, all of these important aspects of understanding our community. So this is just something to consider for the future and for our stakeholder as they are planning, and something to keep in mind. So rounding out to our conclusions for this project, integrating these community-based air quality sensors and the NOAA ports data improve both short-term and medium-term forecasting in the coastal bend. Brandon Forest did predict these good air quality conditions, but Cat Boost provided us with a much better balance with these classifications across the different categories. And our workflow that we have developed through this project and the data set is a great foundation for future air quality projects in this area. And as I mentioned previously, the next step is to work with our stakeholder to develop publicly accessible data and different information. So with all of that, me and Delaney want to say thank you, and we will take any of your questions.
Not all at once, y'all.
Everybody's intimidated.
Yes, Jared.
I know that this isn't the point of y'all study, but I'm just curious if y'all have an answer. For Port Aransas, you had the highest percentage of bad ozone quality, ozone phase, and then you also had the highest ozone reported for Port Aransas. Do you have an idea as to why that would be? I know that's like not the point of y'all study, but
Actually, I do not have an answer to that question. It'd be very interesting to look and see, but it's probably due to a larger influence of shipping traffic, not only with the barges coming in and out, but recreational fishing happening. So those may be emitting more options. Yes.
Yeah, a lot of traffic in that area as well, I would imagine. So potentially that.
Oh, sorry. For the people online, if you can't hear the question, she asked why ozone tends to have a higher percentage of bad air quality. Yes.
So for the, I think the EPA Nowcast predictor, is that like literally their prediction of that value, like for this current hour based on the past stuff, or is it for like a 3 hour in the future or something, or is it literally like this hour?
So the way that I understood it, the EPA does for the current 12 hours. But the TCEQ kind of expands on this and they do more of a discussion based where they say for the next, I think they go up to 72 or 96 hours, depending on if people are in the office to write the discussion. They'll give you an idea of what the air quality will be based on certain things, but they don't give you an exact value.
It's also incredibly difficult to find information, publicly available information on certain emission events that occur in this area, which is a hurdle that we had kind of talked with our stakeholder about and something that they can hopefully implement in the future. Because if you just try to look up any of this information on your own as somebody, as a member of the community, it's really hard to find. So that's just something also to note.
Dr. Sanders, is there anything online?
I don't think so. I think Dr. Douglas is also monitoring, so.
Yes.
No.
Okay, I saw in some of your forecasting skill scores, and I see after 5 days, it's almost flat, sometimes even a little bit higher once it passes that. Do we have some limitation of the forecasting skills for those parameters and we just don't trust it at all? Or can you explain why your forecast skill can even increase after 5 days?
So I assume you're talking about areas where the class imbalance is much smaller, where good maintains. That's probably due to the model overreacting. Because there is so much good air quality within our testing data, it just automatically defaults that it's going to be good. So blind squirrel gets a nut every once in a while. If your good air quality tends to come back, then you can overpredict that. And we see that in some of our options also. For Ingleside, where we have a little bit more bad air quality, we don't see that trend as much. We trust it a little bit. So for the other locations, it would be nice to add more data to our training set, but also expand on the stations just in general.
A question from the chat. So from Blair Sturber Boatwright, question for the presenters. You focused on relative performance with the skill scores. Do you have any absolute scale for a good or bad skill score?
I don't think so.
Okay.
We would need to discuss that a little bit further because I don't think I quite understand the question. But please reach out to us and send me an email so that we can discuss this moving forward.
Maybe you could think about it over the next two presentations
Yes.
and towards the end.
Absolutely.
We have time for more questions.
Yes.
Hi, can you hear me?
Yes.
This is Blair Sturber Boatwright. So, I mean, if you look up the skill scores, 0 is random and 1 is best. And I just didn't know, I'm not that familiar with it, but I didn't know if there was some generally accepted scale that said a skill score of such and such is a good result or not very good result or something like that. You know, I noticed some of your skill scores were hovering right around 0. And I mean, I guess in my own mind that says, well, there may be a difference between cat and random forest, but neither of them are performing particularly well.
Correct. And we truly believe that that specific one. So your first part of your question, a general good skill score, I would say would be anything above 0.5 or even 0.4. But for our specific case, a lot of them are quite low, and we believe that that's driven to the meteorological parameters, not necessarily being a direct description of what's actually happening within the air, and also the lack of bad air quality. So when it goes back to determine whether it predicted it correctly, the majority of the time it's missing those bad air quality. So it's going to pull everything down.
Thank you.
Because our overall accuracy is like 0.8 and 0.9 for both models because it predicts good so well. But we know that that's not a true accuracy because it's not predicting all cases. So we wanted to kind of showcase that.
Right. Thanks.
Okay,
Thank you so much. Can you hold it for towards the end, please? I'm sorry, apologies. We have to change the order of our presentations a little bit. We'll have the BacterAI go next. We really appreciate Cody making it to the presentation today. He is not feeling that well, so we have to let them go next. Thank you. Yeah, we got you, Emily. We can
Great.
see.
Okay, perfect. I want to start by saying thank you to everyone who is attending today. We are BacterAI. So the past 6 months or so, we've been working on our project, looking at how to use machine learning techniques to predict bacterial contamination in Corpus Christi Bay. Next slide, please. So my name is Emily McGee. I'm a master's student getting my master's in marine biology. I've been studying dolphin acoustics, looking at how dolphins communicate and echolocate in different foraging settings. My advisor is Dr. Dara Orbach, and my role on the team has been to help organize us, been helping with the writing and editing, and also some of the earlier data analyses and pre-processing. And my hometown is Iran, Texas. It's a small town in West Texas.
Hey, my name is Mohammed Al-Shalakani. I'm a PhD student in coastal and marine system science. I'm using geophysics, remote sensing, and GIS to investigate how subsurface heterogeneity mediate flooding, recharge, and discharge dynamics during extreme flood dynamic. And I'm working with Dr. Dorina Murgulet, and my role in the team is writing, mapping, and data analysis, and I'm originally from Egypt.
Hello, my name is Jane Ji. I'm a doctoral candidate. My research focuses on epidemic modeling and forecasting in special temporal predator prey system under guidance of Dr. Zadovsky and Dr. Belsivania. For this Bacterial project, I contributed through writing, data visualization, and analysis. My hometown is South Korea.
My name is Cody Lopez. I'm a PhD student. I'm studying hydrogeology under the Coastal Marine System Science program. My advisor is Dr. Dorina Murgulet, and for the project, I contributed mostly with some background knowledge, which is a similar project, and also the coding and the modeling. And I'm from Corpus Christi.
All right, so before we begin, just like the previous group, we want to start by acknowledging all the people that have supported us along the way. So Texas A&M Corpus Christi for providing stages and this opportunity, and the National Science Foundation for funding this program, and our stakeholder, the Texas General Land Office, for collaborating with us, bringing this project to us, and providing our some of our data. Next slide. So now I want to begin talking about the bacteria of interest that we've been studying. The bacteria that we've been studying is called Enterococcus, and this is a bacteria fecal indicator. So it exists in the intestines of warm-blooded species. So we have it in humans, it's in the intestines of livestock, wild animals, and this bacteria, it can enter our ecosystems in many different ways. And when it enters the ecosystem, that can tell us that there is fecal matter in that ecosystem. And so scientists will often use Enterococcus as an indicator of bacteria of how poor or how good the water quality is in certain areas. Next slide. So Enterococcus comes into the ecosystem many different ways. So on the left side, the left figure, we can see some of these sources. So Enterococcus can enter the ecosystem from sewer failures, from runoff, from rain or precipitation. It can come directly from animals such as bird deposits in the water, and come from agricultural places where we have cattle or sheep or chickens. It comes directly from wildlife. Bacteria can also be stored in the sediment, and whenever it's released, it can also re-enter our ecosystem that way. So all that to say, Enterococcus has many different ways of contaminating water bodies. And so in areas where people use it recreationally, such as our bays or our beaches, people that get exposed to high levels of Enterococcus, it can actually pose some health issues or health risks. So Enterococcus can be linked to ear infections or stomach issues, or even some swim rashes. But more importantly, when there's high levels of Enterococcus, that can also indicate other pathogens that may be in the water, which could be even more risky for people to be exposed to. Next slide. So because of this, many different scientists, like the Texas General Land Office, they go out and they monitor these levels of Enterococcus in our recreational areas. But the problem with today's methodology of monitoring Enterococcus in these ecosystems is that it can take a really long time. So what they do is they go out and they take a water sample and they bring it back to the lab, and that can take between 18 and 24 hours and even longer depending on the methodology. But what they do is they look at these samples and they test how much Enterococcus is in that sample, and if it's low, medium, or high, high being greater than 104 colonies of this bacteria. And so whenever we get to that high level of bacteria, the agency will then post a warning out to the public at the beaches that there's a high bacteria count. We probably shouldn't be swimming in this area. But again, this problem is that it takes so long that people may be already exposed to these bacteria, these high levels of bacteria in the water. And by the time we get these warnings out to the public, the bacteria levels can actually already be changed by then. So it's a very reactive warning. Next slide. So our objective was to transform this reactive system of getting these warnings to the public to a proactive approach. So for our project, we sought to develop a predictive model that predicts Enterococcus contamination levels in Corpus Christi Bay, Texas, using environmental, hydrological, and ecological variables. So instead of reacting, we wanted to be able to get these warnings to the public earlier. So like I said, our study site is Corpus Christi Bay. So on the left, we can see a much broader picture of Corpus Christi Bay, and the stars represent some streams that would flow into Corpus Christi Bay that could carry those Enterococcus bacteria as well as other pathogens associated with it. And then all the other smaller figures or symbols represent all the different stations where we collected our data. And so on the right, you can see a more zoomed in image representing the different parks that people will often go to recreationally, which were our points of interest for our project. Next slide. So again, our goal was to develop that model to predict bacteria levels. And the first phase of our workflow was to collect the data. So we had many different data sets, and we went through different resources to combine them into one final data set, which I'll go over on the next slide. So obviously, we needed our bacteria data, which we got from Texas Beach Watch. Then we collected the water level data from the National Oceanic and Atmospheric Administration, or NOAA for short. A lot of our data came from NOAA. They were all publicly available. So the reason why we collected water level is because this can actually affect how bacteria is resuspended in the water column. So as I said earlier, it can this bacteria can actually live and be stored in the sediment. And so water level can actually help resuspend that bacteria back into the water column. And similarly, tides can also move bacteria in and out of the bay. So when there's a higher tide going farther up the shoreline, that can bring bacteria into the water. And it can also transport bacteria out of the bay, affecting the concentration. We also have wind speed that can drive surface mixing, also affecting how concentrated bacteria may be in a location. We have water temperature and air temperature. This directly influences bacterial survival and decay. And then we have current speed and direction. This also moves and disperses the bacteria. So most of these are really going to be looking at the disperse of bacteria, how concentrated it may be in a location. And then we have freshwater outflow and stream flow. These are both
measurements of runoff that could bring bacteria into the bay from streams or from different locations of or water flowing into the bay. So the first one comes from the Texas Water Development Board. These are a mix of direct measurements as well as measurements that came from some modeling, whereas the stream flow data comes from the USGS, which is direct measurements from the Nueces River. And then we have bird presence. It comes from eBird. A lot of people publicly use this to go birding, and they will record when and where they see birds. And so we use this to measure how birds may be influencing the fecal counts in the water. So it's a direct source of bacteria. And then we have rainfall or precipitation from the CHRS. This is obviously a very large factor affecting runoff or storm-driven contamination. And then finally, we have salinity, which was calculated using Landsat data, and this corresponds to freshwater runoff events that can elevate bacteria. Next slide. And so now I'll pass it over to Jane to talk about our next phase in the workflow.
The next step, we cleaned and prepared the data, and they combine it into one file and filled in any missing information. So we use two methods to fill in missing data. The first method is MICE, standard for multiple imputation by chained equation. It is a statistical method for handling missing data by estimating values based on relationship among variables. Instead of filling gaps just once, MICE created several complete data set with a different imputation, then combine the result to reduce bias and capture uncertainty. This slide shows a single iteration of the process. The first, we start this one with a data set containing 3 columns, age, income, and gender. Each of these columns has a missing data, like this one, and this. We can think of age as representing birth count, income as salinity, and genders as categorical variable, similar to how bacteria levels might be classified as high, medium, and low in a data set. In the step 1, we apply simple mean imputation to get the process started. So we filled out 25.5 for the age, and then 12.771 for income, and then gender, we put the F value. And in the step 2, we revert age back to missing data. And then step 3, we use regression to model age based on observed values, income, and the gender, 2 ordered triple, 33, and then 12.771 and F, and the other one is 18, 12, and F. We use this one. And then we get a relationship between these 2 pairs, then we get the input, the age value. So 35.3. We're gonna do this process continually up to we get the old values again. And the next method, we use k-nearest neighborhood algorithm to fill in the missing data. The k-nearest neighbors work on the idea that the birds of feather flock together. New data points are classified or predicted based on the closest existing point around them. This slide demonstrates how k-nearest neighborhood algorithm can be used to fill in missing data. First, KNN identified the data point that's missing here. This is the value we want to input. Then it looked for the closest neighborhood based on similarity in other figures. In this example, there are 3 nearest neighbors, 30, 25, and 22. Once they are found, we take their average to estimate the missing value, which is 25.6. Now I will hand it over to Mohamed, who will explain data exploration, especially the relationship between predictors and bacterial level.
Thank you, Jen. So after downloading, cleaning, pre-processing our data, and merging them into one clean files that we can work with, and filling the missing data, we went back and forth to data exploration, where we plot and graph our data for better understanding of it, and we check for correlation. So next we will go over the correlation metrics we run in our project, and also how these variables impact the bacterial level. So we run two correlation metrics, person and dispersion, between bacterial level and the environmental variables. So positive values here means that the bacterial levels increase with the variable, and the negative means it's opposite trend. So for person correlation, it shows strengths with linear relationship. So as you can see here, we have rainfall and salinity showing slightly a strong correlation with the bacteria. And for person, for experiment correlation, this one is monotonic. Monotonic relationship means nonlinear, but consistently increase or decrease trend. So for this one, we had more variables that showing slightly strong correlation with the bacteria, including current speed and direction, tides, water level, birds presence, water use, as well as rainfall data. So one of the data set we use is salinity data set, and as you can see here in this map, location map showing the salinity on August 1st, 2022 as an example. So the red color here represents high salinity, while blue color represents low salinity. So we're expecting this day that we have low bacterial level because of the higher salinity over the bay. The other one here, the other map here on the right showing the rainfall data over Corpus Christi Bay. Here's the black polygon over here. Blue color represents high rainfall, while red one represents low rainfall. So two things happen after rainfall. First one, adding more fresh water to the system, meaning decrease the salinity and increasing the bacterial level. And the second thing is this rainfall will sweep all contaminant into local base, where it's bringing more bacteria into the system. And this is what you can see on the second map after adding more rainfall. So we have slightly lower salinity over the bay. Here you can see a correlation or relation between bacteria and salinity. So bacteria on the left y-axis represented by black circle, and salinity on right y-axis represented by black dashed line. And also we have three colors for the background. We have green, yellow, and red representing low, medium, and high bacteria level according to Texas Beach Watch standards. So with slightly high salinity, we have low bacteria content, or low bacteria concentration, and with low salinity, as you can see here, we have high bacteria levels as well. Another one between bacteria and bird count per day per user. So with more birds coming to the area, we're expecting to have more or high bacteria level and vice versa. So here we have this area, we have low bird coming to the area. So we're having low bacteria level, and here we have more birds coming. So we have high bacteria content or concentration. And our next step is going to develop models where we train and test our data and for identify the best model to predict bacteria level in Corpus Christi Bay. So Cody will go over these models and why we use them.
So as you guys may have seen from Mohammed and Jane's, including Emily's discussion, we have a lot of different environmental variables available to us. And we needed to include as many of them as possible because the relationships between these different variables and the actual bacteria counts themselves are not extremely straightforward. They're not quite linear. They're a bit complicated. So we began with 3 different types of models. On the slide, I can show you the first 2 different types of models that we use, including a random forest regression model, where where your system will take random samples from your data set and produce decision trees, where each decision tree tries to make a prediction of your final results, and then aggregates these results of all these decision trees into one ensemble model to produce your final results. We also used the histogram gradient boosted classifier model, which helps to make the computer process things a little easier. It takes continuous features, so like long series variables that you have, breaks them into discrete features, and then treats them like a histogram. That's why it's called the histogram-based Boolean model, to produce the same type of decision trees that random forest makes, and then you get an aggregate decision at the end, just similar to random forest, but this one is considered a categorical classifier. We also included an XGBoost model, which stands for extreme gradient boosting, where it also makes decision trees like random forest, but it takes your data set, produces a decision tree, and weights the errors to try and optimize it. So the next decision tree that produces will be designed to minimize those errors, and then creates another decision tree, analyzes the errors and attempts to optimize those again, and then reiterates that process over and over again, and then takes one final average of all these to aggregate as a final result for your model. So we have 3 different types of models going over our data set. These are the results, or well, these are some of our part of the results of the random forest regressor. These are just the R-squared values to give you an idea of how, I guess, how powerful the model was going to be. The average we're predicting, attempting to predict bacteria levels 1 day ahead, 2 days ahead, and 3 days ahead of current actual values. And you can see on our random forest regressor that quickly the model loses its R-squared value, or quickly loses its strength after the 2nd and 3rd day, going from an overall prediction strength of about 0.49 R-squared 1 day ahead to 0.34 average for all of our locations 2 days ahead, and down to 0.26 3 days ahead. And these black lines I included are the marker of 0.5 R-squared, which is generally thought of as like a reasonably good model, and 0.7, which would represent somewhat of a stronger model. So a lot of our locations simply fall below that. So the random forest regressor was not working well for us, but we do have 2 of the model types to look at. We have the histogram gradient boosting classifier, which overall across all 3 horizons had an average F1 score. And these are the F1 scores because these are classifier models. And these scores are weighted because our model also had an unbalanced data set. In other words, there's thankfully a much larger amount of low-level bacteria data points collected than there were medium and high, thankfully for the sake of public health. But that makes it a little more difficult for a machine learning system to try and model these results because most of the data set is low bacteria results. It's going to try and predict mostly low bacteria results. But our F1 scores stayed very stable across 1, 2, and 3 days ahead, which is nice for this for predictive abilities, with a general F1 score of 0.68 for 1 day ahead, 0.67 for 2 days, and 0.67 again for 3 days ahead. So you can see plenty of our locations stayed within what's considered a good model's range of an F1 score. So that was very nice for us, a good result to see. When we looked at our confusion matrix, which shows how well or how accurate, I suppose, our models are able to predict each individual type of reading. So this is on the left-hand axis here, we have the actual values, so where there was actually a low reading of bacteria that day based on our testing data versus what was predicted by the models. So most of the time when there was low values were actually measured, our models were able to predict it about 82% of the time correctly as low. However, there was like a 11% chance they would guess it was medium and a 5% chance they would misidentify a low as a high. So for the most part, it's very accurate at predicting low values accurately based on what the actual results were. When it comes to medium, 67% of the time, they're roughly in the 67% of the time, they're predicting low values when they were actually medium. And for high values, about half the time as well. However, for our models that about a quarter of the time or better, they were actually able to accurately predict high values in the system, but they're not so great at low values, or sorry, at medium values. So an ideal model would have a strong high percentage across the diagonal, and ours is approaching that, but we are trying to continue to improve our accuracy with as much time as we have. We had a third model type. This was the extreme boost or XG boost model type. It also presented very similar F1 weighted scores across the 1, 2, and 3 day horizons. We got an average overall of 0.68 of all 3 horizons put together, with it predicting at about 0.67, 0.67, and 0.67 as the F1 score for 1, 2, and 3 days ahead. So they were all the same, essentially. But even though you can see there's differences among the models from day to day. But thankfully, a nice portion of them were able to show up as what's considered strong models, and plenty of them were in the decent range, though a few are a little underperforming. The confusion matrix of our extreme boost model looked very similar to the confusion matrix of our histogram-based model. However, again, we still are although our model is conservative and focusing mainly on predicting low values, we are able to get those high values right about 0.25% of the time, which is not, which is helpful for us, I think, which we'll actually talk about more towards the our conclusions about how important that can be. But for the most part, these two gradient boosted models ended up being very similar. And I have Jane to talk about a bit of their differences and how we're able to choose between the two models about which is going to be better. So, Jane, please.
When you look at the figure importance in HGB, the top 10 figures together account for 81% of the range. This includes moderate freshwater inflows, salinity, and stream flow from Oso Creek. The tide level and the water temperature and water current are also part of this group. We know these variables matter because they directly affect how long bacteria can survive, how they move through the system, and ultimately, how they deposit into the environment. And the next, extreme gradient boosting model, when figured important is split by percentage. The top 10 figures only account for 47%. So we see a broad spread of the influential variables, like the previous model, XG boosting model include creek stream flows and salinity, but it also brings in temporal figures like months and day of the year, water current speed, and additional component from freshwater inflow from TWDC, such as return to the estuary and river divergence. And despite these differences, none of these figures alone make one model clearly better than the others. They simply reflect different way the model weigh environmental factors. And while both the models perform better than the random forest model, they are quite similar to each other. In total, we made prediction for 3 days across 19 stations, while give us 57 individual models. When we compare them using weighted F1 scores, the extreme gradient boosting outperforms histogram-based gradient boosting in about 67% of those cases. To summarize, both histogram-based gradient boosting and the extreme gradient boosting classifies performs better than the classical random forest model, while the histogram-based gradient boosting and extreme gradient boosting have a very similar overall performance. They differ in the figures they prioritize. Extreme gradient boosting slightly outperforms histogram-based gradient boosting most of the time, but the best model may vary depending on the station and its unique environmental conditions. In importance, both models are good at predicting low values, which means they could help guide when and where to sample more effectively. This work has several broader impact. First, it directly supports the Texas General Land Office, which manages the Texas Beach Watch program and is responsible for posting advisory when bacterial levels are high. A predictive model can help them make more informed decisions and potentially issue warning earlier. Second, earlier warnings strengthens public health prediction by reducing the chances of people swimming during unsafe conditions. Instead of relying solely on the lab results that come in a day late, managers would have a forecast that helps them anticipate high-risk days. Third, model helps identify which environmental factors drive bacterial spikes in Corpus Christi Bay. That information can guide future management actions, whether it improving stormwater control, monitoring certain area more closely, or understanding how rainfall and runoff influence the system. And finally, the end product is a tool that decision makers can use it. It's not just a research project, it's something operational that can be integrated into real-world monitoring and beach management strategy. Moving forward, we will continue doing all we can to improve model accuracy. We also plan to create a simple executable file that the TGLO can use for making predictions. Finally, we aim to share and potentially publish our methodology and results to support broader understanding and future application. Thank you for your time and attention. We'll be happy to answer any question you may have.
This is Lucy with the Texas General Land Office Beach Watch program. Thank you for doing this. I do have a question about your models. On your presentation, you talked about how the models were accurate at predicting low bacteria levels. What was the percentage of accuracy at predicting advisories? So anything over 104 bacteria units for Enterococcus.
I would probably have to go back to actual results to try and figure out what the actual accuracy value is. But when it just comes to what our confusion matrix was predicting, it was able to accurately predict from its testing data high values of bacteria as high values about 26 to 28% of the time. If that hopefully provides a bit of an answer towards your question. But for the actual accuracy, I can pull out some better numbers after the presentation when I get back to my results.
That would be great. I'm very interested in that because as the project manager for this program, a way the GLO could potentially use your models with higher accuracy is it would help us coordinate our resampling and how we use our field staff, and in turn it could actually help us save money and use those resources in other areas of interest. So I appreciate the work you guys are doing. Thank you.
Thank you.
For those of us here, I'm sorry, I'm not sure why the audio is coming out very quietly.
Any other questions for our BacteriAI group? Yes.
I like y'all's presentation. Is there, on the selection of variables within the models, I was just curious if like water temperature or like nutrient concentrations in the bay. I know it's easier to like throw out variables that you'd want to put in, but finding the data, are those like feasible variables that y'all think might have a effect?
Nutrient data would probably be impactful, but I think for the most part, it's probably going to be hard to find one with a frequency that's going to be helpful to the model. What we were really trying to find that we were still frustrated we couldn't get a hold of was something to help us represent how like the presence or increase or change of population of people at the coastal areas, or even like data from like how many people are at parks or something. We tried a couple different avenues, but we kept hitting dead ends of trying to get something like that. If we could find, if anyone has one, we'd love to throw that into our model because the presence of people on the beaches or people walking their dogs or people just generally being there, contributing potentially to wastewater approaching the area would be probably really helpful to our model.
Oh, yeah, I realized that.
Yeah, but Cody is right, there's not sufficient nutrient data at the same resolution, but I think that's something that Lucy is working towards adding to the database. Right, Lucy, if you could hear me?
That is correct.
Because it's important. They're related, of course. Any other questions? If not, I think we can take a 15-minute break. Audrey, is that what we have?
10 minute.
10-minute break, and then we'll resume for our third presentation. Thank you. Thank you.
So, as everybody's coming back in from the break, we are ready to go into our third capstone presentation. For that, I will hand it over to Jerica and Sophia.
Okay, good morning, everybody. Thanks for sticking around and for being here today for not only us, but our fellow trainees. Today, we're going to be talking about our presentation or the project that we've been working on for the past 6 months, which is called Do Some Thunderstorms Bring Their Passports? And we're looking at tracking cross-border convective systems from Mexico into Texas. And before we get into it, we of course want to acknowledge everybody that helped us finish this project up. So we want to thank, of course, Stages and TAMUCC for funding this project. And we especially want to thank the National Weather Service and Nick for being so helpful throughout this project. And now we can get into it. First, I will introduce myself. My name is Jerica Rusili. I'm a second-year Coastal and Marine Systems Science master's student. My advisor is Dr. Liu, and my thesis is looking at isolated versus organized precipitation around the globe using GPM. And my background is that I have a bachelor's degree in environmental science from here, TAMUCC. And I'll pass it to Sophia so she can introduce herself.
My name is Sophia Mihalik. I'm a second-year marine biology master's student, and my thesis is investigating early life history traits of native and non-native damselfish in the Gulf of Mexico. And I'm advised by Dr. Majoris and Dr. Walter. And I have a BS in biology and a BA in earth and environmental science from Lehigh University. And I'll let Jerica go and introduce our project.
Okay, so the question that we are trying to answer with this project is one that the National Weather Service brought to us earlier on in our Stages journey. So they brought this problem to us, which is looking at how thunderstorms propagate from Mexico into Texas. So they have a lot of trouble looking at these types of systems, largely because the radar coverage in this area is limited. If you look at this blue box here, this is our study area. You will get a better view of it later on in the presentation. But you can see that Mexico, and especially in this middle region of the Texas border, we don't have as much radar coverage as we'd like. And this makes accurately predicting thunderstorms in this area a little bit more difficult. So the question that we're trying to answer is how and under what conditions do thunderstorms originating over the mountainous terrain of Mexico progress into Texas/the Rio Grande Plains? And before we get into how we're trying to solve this problem, we can talk a little bit about these thunderstorms. So these thunderstorms happen mostly because of orographic lifting. What that means is that we just have moist air coming in from the Gulf, hit the Sierra Madres in Mexico, and this air will lift and cool. And since it's moist, we can get some thunderstorms happen. In some cases, these systems can grow into things such as mesoscale convective systems and bring severe weather to our area. So an example of this is happening. It was on May 9th of 2014. If you look at this GIF that we have here, we had a lot of rain in this event, and we also had some flooding that happened as well. And these storms happen most commonly during our warm season, specifically from May to July is when we see the most activity. But anytime when the air is warm and moist, we can get these types of storms. So with that being said, we can talk about our project objectives that we came up with in conjunction with the National Weather Service. So first, we wanted to develop a storm tracking algorithm so that we can actually see the tracks and see how these storms are moving. We then wanted to analyze the tracks using the radar-derived variables that we have with our database that we'll get into a bit later, and look at the large-scale atmospheric conditions in which these systems occur. And then we also wanted to create a predictive model to see if we can tell when storms are going to propagate into Texas, or if they are going to die out before they actually reach the forecast zone. And through all of this, we are collaborating, of course, with the National Weather Service here in Corpus Christi to align our product with their needs. And now I'll let Sophia talk a little bit about the project impact.
So this project is very relevant, especially since we are in South Texas, and our goal is to improve storm prediction. And so if they're better able to predict these storms, the National Weather Service can send out alerts to the community with more warning time and with more confidence and accuracy than they could before. And so this would enhance emergency response, flood mitigation, water management, and build climate resilience across the Rio Grande Valley. And this would affect up to 1.3 million people that live in South Texas, and they would benefit from this enhanced forecasting, and it would also build better trust with the public, and it would reduce harm to people and to buildings, and reducing costs that the government would have to pay for rebuilding infrastructure or healthcare costs that could be a result of storm damage. And now we'll get into some of our methods. So we wanted to introduce the sources of data that we're using. So we use 3 different data sources in our project. Our first one, we use the multi-radar, multi-sensor convective feature database. Now, from now on, we will call it the MRMS-CF database. And so that is curated by Dr. Chantal Liu at TAMUCC. And so we use this for identifying, classifying, and tracking our storm systems. We also use the University Corporation for Atmospheric Research Radar Composite Archive, or the UCAR Radar Composite Archive, which shows radar image loops that we use to identify our storms as hit or miss, which we'll get into further. And then finally, we use the European Center for Medium Range Weather Forecasts, Reanalysis version 5, here on known as ERA 5. And so we use this to identify large-scale atmospheric conditions and get our environmental data to match our storms. And so just briefly, this is our project workflow. We first had to identify our storms. Then we had to classify them as hits or misses. We had to track them for their entire length and create that storm tracking algorithm as part of our objective. Then we did some filtering and quality control of our data, since we had to match it with the ERA 5 data. So we had to make sure that everything matched and that all of our storm tracks had correct data and that all of the terms were filled in. We did not do any data filling, since the data that was missing for like an entire storm track, so we can't just fill that in and create false data. And then we used our machine model and implemented it. So diving deeper into our methods, the first step we had to do was define our study area and filter for convective features. So we defined this study area in conjunction with the National Weather Service to identify the area where these storms are coming across the border. And so we filtered the MRMS-CF database for days with convective features in the study area during the warm season, so April to September from 2017 to present. 2017 was the start of this curated database, and these convective features, there's a definition on the handout, but it is a storm that has a DPZ of over 40, which is a measure of the radar reflectivity that measures how strong the storms are. So we wanted to make sure that we weren't picking up storms that were too small or that were just a light drizzle. We wanted to make sure that these were actually strong thunderstorms. The next step in this, so kind of continuing, is we looked at the total rain threshold for each day. So each day that we had identified, we looked at how much rain they got. And so we decided on the threshold for how much rain we had to be able to look at the UCAR radar image archive. And so we knew days, we did this in May, and we knew some days that had some thunderstorms and days that didn't, that were just a light drizzle. And so we looked at how much rain those had and kind of decided on a arbitrary threshold, just enough that we got all the thunderstorms, but not too low that we were looking at every tiny bit of rain. So we did this to make sure that we weren't analyzing too many days, since it took a while to go through all of the image archives, which Jerica will get into.
Okay, so yeah, moving on to looking or verifying these CF days using the UCAR radar image archive. Basically, what we did is we went through every single day that we initially decided had a substantial amount of rain, and we looked at these radar loops and decided if the storm was a hit, meaning we saw clearly that the system moved from Mexico into Texas, as the example is showing here, or miss, meaning that we saw that rain did start in Mexico, but it died out before reaching Texas, or if the rain that was detected was unrelated to the specific phenomena we're trying to study. So it could have been a frontal system that moved in, or sea breeze storm, something like that. We weren't trying to study with this specific project. So we went ahead and ignored those days for now. And so once we had our radar days, or we had our storm days verified, we went ahead and used those CFs to create these storm tracks. So how we did this is our CFs had to meet the following criteria. So the time difference between CFs had to be less than or equal to 15 minutes in order for us to connect the two convective features together. And they had to overlap based on their size. So this specific size might vary depending on the size of the storm. And once we had those initial checks in place, we created storm tracks, but it came up while we were doing creating these storm tracks that it looked like maybe some of our storms could be fragmented. And this could make sense because we're using a 40 TBC threshold. That means that the rain is going to be pretty intense. But sometimes throughout a storm's lifespan, we can see strengthening and weakening of the storm system happening. So we wanted to make sure that we weren't counting storms as separate storms if that was occurring. So we used this fragmentation check where we're just seeing if a storm is within 7 kilometers of each other and less than 15 minutes of each other, we went ahead and merged those two separate tracks into a single track. And then again, we used that hit-miss classification logic. It started in Mexico and died out before it reached Texas. That is a miss. If it made its way successfully into Texas, then we're calling it a hit. And this is an example of those types of the storm tracks that we created with this algorithm. So this was for May of 2024. You can see that we have our orange tracks that are misses and then our blue tracks, which are hits. And so once we had our storm tracks created, our next step was to go ahead and collocate some AERA5 data to our storm tracks so that we could actually look at the environmental conditions in which these storms occurred. So we first had to generate our AERA5 data requests. We did this simply by looking at the time and the area in which the storm tracks occurred and downloading data for those times in that area. And then we collocated it to match the closest time and space. And then we interpolated AERA5 to each storm location, and we did this for 3 different time offsets. So we did this for 3 hours before we first see the storm initialize, an hour before, and then at T0, which is basically at the storm initiation. So once we did this, we get this very large list of ARA5 variables. I know this looks like a lot. Just to put it in simplest, very briefly, we have things like temperature variables. We have things like cloud base height, CAPE, SIN. All of these things are important in when it comes to storm initiation and propagation. We also have variables that are like near the surface, variables that are specific to certain pressure levels. And then we have our calculated variables such as lapse rate and wind shear. So we went ahead and calculated these variables after the fact using the ARA5 data in which we collected. And I'll let Sophia talk about how we did the modeling part of this project.
Luckily for us, our other groups already kind of explained some of the models that we use. So we use random forest and gradient boosted regression tree models, including XGBoost. And we trained using an 80-20 train test split, meaning we used 80% of our data to train the models and 20% to test the models. And as you can see on the right, there's an example of a decision tree. This one is very basic, but this kind of shows the basic logic of a decision tree. It splits the data into two different categories, and this just bins them directly from here, but it is controlled by multiple levels, and they combine multiple trees after each other. And the gradient boosted regression trees learn from the previous mistakes. So if one tree made an error in classifying, then the next tree would hopefully improve that previous tree's error. And in our testing, we used cross-validation, smoke resampling, and hyperparameter tuning to improve model performance. What this means for the cross-validation is that we separated our data into 5 different groups. So 20% of our data in each group, and that is randomly pulled from the sample each time. And we did that 3 times. So we did 5 samples 3 times to get 15 runs for each model. The smoke resampling is a way to balance the classes as we had way more misses than we had hits. And we did hyperparameter tuning, which is explained here. So there's different model configurations, like how fast the gradient boosted regression trees learn from one tree to the next, how many trees they use, which is known as the number of estimators. The learning rate is how fast the trees learn from each other, or how many decisions it makes in each tree is the max depth. So we had an automated way to do this using grid search. And so this tests several different values for each of these and shows us the best one. And so we took these results and then implemented them into our final models, as this grid searching is very computationally and time expensive. So we took it out of our final model and just used it for testing. And so getting into our initial results, these are our results from the MRMS CF feature database results. And so we looked at when the tracks started during the day. We can see that a lot of them are concentrated in the evening hours, which we expected, but there isn't significantly more hits than misses at any specific time point. We can also see that there are more storms occurring in May and September than the other months. But there, again, wasn't a specific trend in having more hits than misses or having one month where all of the storms were. We also looked at the spatial distribution of hits and misses. So starting with the density of hits, there's this little buffer period around the border. And so most of the storms that were hits kind of started in this southeasterly area, probably driven by sea breeze and moisture coming in from the Gulf that helps propagate the storms. But there are less storms making it over the border in this more northern western area. And then compared to compared to misses, more of the misses are occurring in that northwestern area. And then there's a gap right here that's possibly due to the gap in radar coverage that might not be actually due to a lack of storms. And then again, there are more misses concentrated around this southern area of the border, probably driven by that sea breeze again, as well as the moisture leads to more storm initiation. And I'll pass it off to Jerica to discuss our machine learning results.
Okay, so this table is just a really quick overview of our machine learning test results. So we tested our model at the 3 different time offsets, and then we combined all 3 time offsets just to see what the results would be. This is a bit much to look at. So we have a bar chart to make things a little bit more readable. So the first thing I will point out on this chart is that the red colors are going to be the random forest. The blues are going to be the gradient boosted regression tree, and then the yellows are going to be the XGBoost. And there's 4 different ones for each one because we have the model at T-3, T-1, and then at T0. And then of course also at with the 3 combined. So the darker colors on this chart are going to represent the combined model. And with our test model performance, it is looking like the random forest and the XGBoost are performing the best at this point. And that is likely because if you look at the false alarm, you can see that the gradient boosted regression tree has a much higher one than the random forest and the XGBoost. So that ends up causing it to be less accurate overall. And whenever we're looking at the CSI or the critical success index, you can see that, again, it's not doing as well and that the random forest and the XGBoost are doing better. So at this point, though we are seeing that the random forest and the XGBoost are slightly outperforming the gradient boosted regression tree, they still are generally performing similarly enough to where Sophia and I decided to go ahead and pull a final model for all 3 of the models just to see what the final performance for each one using the best hyperparameters would be. Before we get into that, we can talk a little bit about the top 3 predictors that we saw during our testing phase. So for the most part, 41.7% of our feature importance when looking at these models, freezing level height was in the top 3 predictors for the model. So at this point, we're seeing that freezing level height is very important, and we'll get into why we think that is when we're looking at the results of our best 3 models. And then we're also seeing that the low level U component winds or east-west winds are also coming to be very important. And other things that are important are 2-meter temperature, our relative humidity at 850 HPA, and dew point temperature. But for the most part, we're seeing that freezing level height and the U component winds are already being showing to be very important for how the model is predicting a hit for steadiness. So these are our final machine learning results. And as you can see here, we're still seeing the, with our best hyperparameters selected, we can still see that the random forest and the gradient boosted regression tree are performing very similarly at this point. But whenever you're looking at the false alarm rate, the gradient boosted has a higher false alarm rate than the random forest and the XGBoost, which leads us to believe that the random forest might be the best choice when trying to deal with this specific problem, especially when we look at the critical success index. Though they are similar, the random forest does have the best score. So we think that moving forward, the random forest might be the best option for dealing with this problem, but we're still going to go ahead and show you the results for all 3. So first, talking about random forest, we'll first look at the confusion matrix. So we have the actual case on the left, and then on the bottom here, we have the predicted. So When it comes to predicting misses, we have a probability of detection of 0.76, and for hits, we have a 0.75. So this model is a bit more balanced in its predictions for both hits and misses, and its false alarm rates, as you can see, since the detection rate is similar, so are the false alarm rates. So this is our most balanced model, which you will see as we show you the other two. But when we're looking at the top predictors, the most important predictor ended up being the low-level U component wind. And this is likely because this strong east-west flow near the surface can influence storm motion. So if there's a strong east-west wind near the surface, that means that the storm might be able to better move into Texas versus if there's not as much wind. Another thing that proved to be important was our 2-meter temperature. And this is likely because if we have warm temperatures near the surface, then that supports low-level instability, which means we can get storms. That's why, in general, we get these storms during the warm season and during the warmest hours of the day. Another thing that seemed to be important is freezing level height. As we mentioned previously, this is likely just showing that because when you have a higher freezing level, you have a deeper warm cloud layer, which allows you to have stronger convection, which will allow these storms to be more strong and be able to last longer so that they're able to make it into Texas. When we're looking at the gradient boosted regression tree, you can see that the top 5 predictors are actually the exact same. The only difference being that the time offset for freezing level height, it picks slightly different time offsets. But for the most part, the models are aligning well with what they think are important for predicting hits and misses. But when you look at the gradient boosted, if you look at the gradient boosted regression tree for the computed matrix, you can see that this model is actually better at predicting hits than misses. This was a surprise to Sophia and I because if you recall, our data is actually, we actually have more misses than hits in our initial data set. And this at the beginning was a bit of a problem, but the smoke really helped us balance this data set out, especially the gradient boosted regression tree. As you can see, it ended up being better at predicting a hit than a miss. But with that, we also do have a bit of a higher false alarm rate. So it's more likely to accidentally predict a miss as a hit. But depending on what your overall goal is, if we want the community to, if we'd rather them be overly prepared than underprepared, that might not be so bad of a trade-off, just depending on what the National Weather Service's goals are. And when we move into XGBoost, we are seeing the opposite when we're looking at the computed matrix. So this model is better at predicting misses than hits, and this is what we saw for most of our training with all 3 models, but at the end, the XGBoost was still better at predicting misses than hits. And another thing I'd like to point out with this model specifically is that we actually do get a different variable in the mix here. We have temperature at the 925 pressure level. So this, we think, is because it can control low-level lapse rates. So if we have warmer temperatures at this level, then we can, it can favor deeper vertical mixing, and then that could maybe allow the storms to grow. But those were our major takeaways for these 3 models, and now allow Sophia to wrap it up.
As you saw from our results, this is a summary of all of the top predictors from our final models. So the freezing level height, low level winds, and temperature related predictors were our most important features. We want to note that these may not be as important in actuality and for storm propagation. So these are what's most important for our models to choose whether the storm was a hit or a miss, but this isn't an actual experiment that's going out and testing these. So we can't say for 100% certainty that these are the factors that are causing a hit versus a miss. So we wanted to emphasize that point, that we understand that these might not reflect what's going on actually in the environment, but due to the very consistent results from all of our models and across all of our testing phases, we really believe that these could be important and could lead to future experimental tests testing the importance of these variables. Now, going into our next steps, we will work with the National Weather Service to help implement our models in their workflow. And we want to publish our results, and so that these results could possibly inspire others or lead others in areas that have difficulty in weather forecasting to use machine learning models where applicable. And so in conclusion, we wanted to note that machine learning is a very valuable tool in big data analysis and can really help clarify situations that might not be explained by traditional statistical methods or linear relationships between the data, such as in this case. And our model results are promising, and so we have decently high accuracy while maintaining a relatively low false alarm rate. While it's not 100% perfect, we think that they are very promising and they can be used experimentally and they can be implemented by the National Weather Service forecasters in conjunction with their traditional numerical weather prediction tools and expert judgment. So we don't want our model to be taken alone and completely 100% trusted, but this can be a tool to aid and advise the forecasters in their prediction. And from that, we would like to thank everybody for listening and thank again TAM-UCC, Stages, NSF, and of course the National Weather Service, and we're open to questions.
Any questions? I would like to mention that they will be presenting their results at the upcoming conference. What is the conference?
Yes. Yeah, so for those online, we will be presenting our results at the American Meteorological Society conference in January.
And so are our Airware group that presented first. And this is the first time we have groups wanting to present their research from this experience, and we are proud of you. And I know you're wanting to
Ron, do you have a question?
There might be feedback.
Hopefully it's not right, people.
Can you hear me?
Yes.
All right. First off, Jerica and Sophia, really excellent work. Really excited to see your project move along and the results that you were able to come up with. I thought it was fascinating how you were able to document so many misses that occurred, with storms in Mexico that do not cross into Texas. And so that's something we certainly observe as meteorologists, and that's the challenge is, which of those storms are going to be the ones that cross and produce that are dangerous, produce damage and impacts to our South Texas community. I was a little surprised and glad to see the results and the variables that you were able to identify, with the low-level winds, the low-level instability, the freezing levels all being potential predictors. And so I think, going forward, it'd be really great to examine that in more detail, to see if there might be a range of meteorological values that we can look for as meteorologists to see, days when those parameters are in place, and we might be able to better predict, in looking at the model data every single day, when today might be the day, for storms to move across. And so anyway, very, very excellent work. Really loved how you presented it. As being non-meteorologists, you guys sounded just like a meteorologist. And so really great work by the atmospheric science team there that you have at Texas A&M. We appreciate all that you do to help us out. So great work and thank you.
Thank you.
That was the meteorologist in charge of our local.
Yeah. That's my boss.
Yeah.
Thank you. And so we wanted to point out this is kind of supplemental and maybe more important for you, John, and the National Weather Service. Something that we also calculated was the SHAP values for each of our final models. And so these look at the most important variables, and each dot is an individual test case, and it tells you the value and kind of the impact on the model. So if it's a lower value, or the SHAP value, so it's tells you how the feature really impacts it and the value of the feature. And so this can really dive into how exactly each individual case was determined in the values that led to it being classified.
Excellent, thank you.
I'll make a comment and then ask a questions, actually not to the students, but to the
Yeah, but we also, so we're asking questions for this group, and then feel free to roll into asking questions for the other groups as well, or for about the program and so on.
Okay. It's a really good job on the AI. Love the design, how you went about it, etc. And really good job also on explaining what variable importance for machine learning. And this is a strong possibility, something great information, but not necessarily directly to the process there. And so my question is on the variable importance, and kind of also for Nick and Chantal there. How much do you think correlations influence? Like you have some correlated variables there. Would you regroup them? Maybe if you have some of the variables are mentioned several times there, they're not at the same height, or they're not exactly like, what would you, should we regroup them to give the importance of that particular variables? What do you think?
Yeah, so some of them are listed, or it might appear that they're listed multiple times on the feature imprints because they're listed at different time offsets. And then we didn't necessarily take out any variables like the other groups did to reduce collinearity due to the decision trees taking random features that we did research, and it said that for the decision trees and the random forest that we didn't need to reduce multi-collinearity.
That sounds good. That would be a discussion with the expert there. But my second question is on SMOTE. So I really like the use of SMOTE. Are your final results also based on SMOTE samples? So sort of realistic but artificial ones. So that was part of the testing?
Yeah, we use SMOTE in both the testing and the final models.
When your final POD or your final confusion matrix includes SMOTE data, SMOTE generated data.
Yes.
Could that have brought up the performance a bit?
That could possibly be why. Whenever we were doing the testing of the model, we would test several different hyperparameters at a time, and we would necessarily look at the specific like metrics for every single run. We would just get like an average based on the different parameters we tested, and they were typically lower than our final model results. So that could possibly. Yes.
The major data set is the radar. Are you using any surface rain gauge? Is that going to be helpful?
No, we did not use any surface rain gauge, and we actually didn't really think about that, but that could be cool. That could be interesting to add into the data. We didn't end up using any of the radar-based variables in our models because when we discussed with Nick, we thought that might be something that they wouldn't have access to when trying to use this model in real time. So we wanted to just include things that we thought would be useful for the National Weather Service. But before we did that, before we just used the ARO5, we did include the radar MRMS variables, and the models were performing better with that data than just with ARO5.
Yeah, the theory was that we necessarily, like, we know we'd have the radar data in real time in Mexico at initiation. We want to make the prediction at that time, so we couldn't use that as a predictor because we wouldn't really know it in real life what the radar data would look like in the future, because otherwise we wouldn't need them up. So yeah, the gist was we wanted to have everything to where we could have all the inputs at a time where we really could have all the inputs in real life when we actually running the model, basically. So that was why we focused on the radar features at initiation and before initiation, nothing after.
Yes.
So I can tell that you have three strong predictors. One is the freezing level height, and the U at the surface, and the temperature. And could you design a model only rely on those three parameters and for a quick operational process? Because many times when we on the real time, you don't want to get 100 parameters to put into the model. And what would be the model performance if you only use three parameters with plus minus 1 to 3 hours, then get that performance? And if that can give you a pretty good shot, then we can implement it online and make it online too.
That's a very good suggestion. I'm sorry, I forgot to repeat the questions online, but Dr. Liu suggested that we try creating a model with just the low level winds, the freezing level height, and the temperature, since that is continuously very important predictors to see if we can achieve good performance so that it can be a tool that we could post online. And that's a very good suggestion. That is definitely something we could try, and we already have the model, so it wouldn't take much work to just only use those three. So yeah, thank you.
Any more questions for this group?
I actually have a broad question. Neither of you guys have a ton of atmospheric science background, so what did you find the most interesting about this entire project?
I found so many things interesting, and I've been learning a lot. I guess I will mention I do have a minor in atmospheric science, but I obviously still didn't. I didn't come into grad school with that much experience. I've been learning a lot through my thesis work and also through this. So I think something specifically that's been interesting is learning more about like the local climatology and weather. I actually didn't really pay much attention to these storms specifically before starting this project, so it's been cool to like check the weather and see these storms propagate. And yeah, so I would say that. But Sophia had less experience.
Yeah, one of my degrees is in earth and environmental science, but I didn't really take too many. I took like one atmospheric science class, and I'm getting a master's in marine biology. I think it was very interesting to learn about all the different factors influencing storm propagation, and like Jerica said, like applying it into real time, like being able to over the summer being like, oh, there's a thunderstorm coming, like let me go check the radar, like watch it coming in real time. So that was very interesting, and to learn more about the weather here. I'm not from around here originally, and I didn't know about this issue or even that thunderstorms happen here a lot. So it was very interesting to learn about the local environment and the local challenges.
And we both really enjoy watching the radar loops.
Thank you. Thank you so much. But I think the question you asked applies to you also. The other group. So we'll start with you. How about you?
I'll let you go. Well, I'm not an atmospheric scientist, so I actually enjoyed learning from my incredible partner, Delaney, and I didn't have any idea about, local forecasting or even monitoring of pollutants in our air. And I think it's honestly made me a more knowledgeable community member. So I think that that's something that I've taken away, and it's given me a lot of skills learning from Delaney or from Jerica and people that I probably wouldn't have crossed paths with here at TMU-UCC, and being able to work so closely with all of them. So I think that that's my big takeaway.
So my biggest takeaway, I do have a background in atmospheric science, so I kind of knew what to expect going into this project. I definitely feel like a more well-rounded community member, knowing all of the issues that are pressing. But the biggest thing that I took away from this was actually getting to work with Jasmine and her lab outside of a project directly related to stages. I actually got to participate in another master's student, Kyle King's sampling this summer. I went offshore and helped him fish, and I got to see the different aspect of the ecological side, not necessarily directly from the atmosphere. So it was cool. I was really grateful for the opportunity to branch out and not just stick in what I know. And that was my biggest takeaway.
Amazing, amazing. Mohammed.
For me, I have no idea about bacteria before I joined this. Mainly focus on applied geophysics, mainly near surface geophysics, go outside, collect data, and dealing with the subsurface. So it was great to be in working with this team, especially Rudy has a very good experience on bacteria. So I learned a lot, and now won't think too much before going to the beach. Because I'm a father now, like 2 weeks.
Congratulations.
Yeah, thank you.
Yes.
Yeah, it was great. It was great experience, and looking forward to it.
Jean, I know, I want to say something that Cody and Jean are both full-time. They have full-time jobs on campus, and this was on top of their PhD project. They did their best to work together on a project outside Jean's area, and she also passed her qualifying exams and proposal this semester, so she's a candidate too. Congratulations to all of you. They worked so hard to make it here, but they did a really good job. So what was your, I know coming in, it was a lot of anxiety and you still have it, but did it help in any way?
Every time I try to make an equation as a model, but this is a kind of first time to build the model in the machine learning.
Okay.
So first time I was really don't have no idea why this is a model. Is why they call
An
this is a model.
environmental,
Yeah.
more of on the environmental side? Okay.
Without any the mathematical equation, they call this is a model. But now I understand it, and I really enjoy it. It's a little simpler than the math. So I like it.
Okay. Emily, can you hear us?
Yes. Huh?
Can you speak to your experience?
Yeah, of course. So my experience with stages has been really great. It helped me get a job after, because I'm graduating this semester. But I think the two things that I've taken away the most, or maybe three, I really enjoyed learning about AI and machine learning. I'd never, I guess I had a little taste of it in my thesis, but taking environmental forecasting and just doing all the data pre-processing in the summer really helped me grow as a scientist and learn new ways to study large data sets, which I think is a really valuable skill set for our field. I also learned a lot about teamwork, working with a large group or four of us, and learning how to work with people from different backgrounds and drawing from each other's strengths was a really great experience. And then I also really enjoyed the field trip because I was exposed to geophysics, which is not anywhere near my field of expertise. But Mohammed really was able to teach me well and help me understand their field work and how they analyze it and stuff. And I was able to present that to our class. So that was really fun and interesting. So yeah, that's pretty much my experience.
And also congratulations to Emily who defended this semester and Emily, you are also like to start working, right? You got a job, Hopper?
Yes.
Can you tell us where?
I'll be working at White Oak Conservation. It's a conservation center in Florida.
Okay, congratulations. Thank you for sharing. Thank you. And thank you for being here today.
Of course.
Okay. open to other questions. Please feel free. Say anything? Do you want to say anything about your experience?
Well, just overall, it's been a real pleasure. As we've already gushed and said, we're very proud of y'all as students, especially. You guys have done a tremendous job. And I think what has just been really great about everybody that's been involved with this program has been the openness and willingness to learn from each other and to operate from a strengths-based position, and having really in-depth dialogues and discussions. And I think just along the way, just being really intentional with how we're thinking about things and trying to integrate past, present, and future, as well as being mindful of, again, the diversity of the backgrounds of everybody involved, but also being mindful and respectful about the stakeholders' positionalities and the general public, I think has just been really valuable. And so I think professionally and personally, it's been really great. And so dare I say, this is a unicorn model that I would hope can very much continue. And so again, thank you. It's been a real pleasure learning from you all and contributing where possible.
Likewise, thank you for joining us and helping us along the way this year. It's been a great experience, I think, for the students and us, myself, learning a lot. Thank you. Anything else? Yes.
I have a question to our stakeholders and the discussion that started. We very much want our model, our science to be used by the stakeholders, but it's also really difficult. It's called the R2O process. It's called the Valley of Death, and we'll have a talk on that at AMS. So for example, Nick, how can we, what's that transition? And it's really important that both sides understand well their role. If one side say they can do more than they can actually do, it's not going to work. The other side, so we need a good coordination, and I think this NRT program can help.
Yeah.
So
yeah, definitely having had experience on both sides of the equation, the R2O is very difficult. But in this case, with this specific project, to actually work with them to say, okay, this is what we'd have available in real time. This is what we could use as a substitute for the ERA in real time as the predictor space of you similar enough that you. And then this is how we could potentially implement it, how we'd get this data, how we'd output this data. And so you got to think about all that stuff. And I think if you go into a project, you think about that from the beginning, it's often better than like, oh, we have this model, but oh, we need all these predictors. Oh, this one won't be available in real time. There's no way we could get this. We couldn't run this. So I think if you go into it thinking, okay, this is the limitations I'll have in a real-time operational environment. And also, like, what does the output look like? How do you format the output in a way people can see it, rather than just, okay, we'll calculate, oh, the statistics all look good when you ran the model, but how do I actually get it? And will people understand the output? In this case, it'll be a probability, so it should be, but do they understand the limitation of the model too? Like, this is predicted based on this. This is what the model was trained to predict. And you also have to make that clear with the operational people that this is what the model is not predicting this, it's predicting this because this is what it was trained to do. I think sounds the operational side, the stakeholder, you may think the model is trained to predict something else like than it actually was. So you have to be kind of specific enough with the problem, like we can expect the model to do as well as advertised with this specific case, but if you want to do it for something else, it may not be the same. So that's my experience having done this before with my own research, and then also working in operations for many years now, is if you go into it kind of the project planning on on something that could be easily implemented in operations, it'll make your life a lot easier. And vice versa, if you're in operations, make sure you at least know like what the model was trained to predict when you're using it, because that'll help you a lot.
Cool. Super. And that's convergent science. And I think as this group, if we want to go after after funding, that is something that is kind of hot for the reasons that Nick just said. If You gotta have everybody together at the problem definition, because otherwise you're gonna be using variables that they can't use when they implement. Do you think you can implement the Jerica and Pia's models?
We actually had talked a little bit about it. I think Jerica will actually be available for part of next semester. Is that still the case? Yeah. So because we thought like, okay, we can use this as a surrogate for this data set. We can use this is how we can get when initiation occurs to run the model. We can use this radar data set to see that T0, and then we can get this data set. So and then how do you output that? And in this case, it'd be percent chance that this convection. And the really useful thing about that is the operational uses. They show that the time it initiates. It often initiates over Mexico around like 3 to 5 p.m. And it gets here in like the evening and overnight sometimes, by the time it makes it all the way. And our staffing is typically the least in the overnight period. So to be able to issue those warnings and stuff, having this knowledge available, like this is a higher probability day this stuff does make it, will give us the ability to like hold people over, have extra staffing for that overnight period. And that's really, I think, one of the key operational uses here is for us to be able to staff better, because we'll know, okay, the stuff that's developing at 3 or 4 p.m. when we usually do have a lot of staffing at that time. The problem is the storms take a while before they actually get here from when they develop. Usually it'll help us like say, hey, today we should hold someone over because we're gonna need extra bodies to issue warnings and stuff overnight. Or hey, today it looks like it's probably gonna be a missed day. We can go home, we can have our one person working overnight and it should be fun. And so with other tools, obviously, that they mentioned, we have numerical models. They don't usually forecast this specific type of weather well. That's why we did the machine learning problem. And that's another thing with the research operations is there has to be an actual problem. And I think all of these groups did a really good job, like especially you two that really have no predictive, that there is no prediction. It's all post observation and stuff like that. In this case, we do technically have models that forecast this phenomenon, but they don't do it traditionally very well. So that's what we did. So
cool, thanks.
Yeah, so Peyton, from your perspective.
Yeah, so actually we've had multiple conversations about that, how we can go forward with this modeling. And we have a dashboard that we are working with an NSF grant with UT Arlington. And we've already discussed about incorporating this into that dashboard and also plugging in more data parameters, not only from what's been recorded between, when I first provided the data and now, but we're also expanding our air monitoring program with that NSF grant with UT Arlington. They're building 30 of their own air monitors that they want to deploy all around the coastal bend. And then in a separate funding, we also received some funds to have up to 5 regulatory grade particulate matter monitors that we're wanting to deploy. We have the first one already that's in boxes currently. It's after we get past the special use permit thing, we'll be assembling that and deploying that in the field. So a lot of data, and hopefully it'll all mesh well and incorporate into that format.
Peyton. Lucy, I don't mean to put you on the spot. I know you're extremely busy, and the conversation will continue with you as part of our projects, but also, looking further into the model that the group works on. What are your thoughts and needs? And I know it's really complex. We're trying.
Yeah. So for Beachwatch, we're definitely looking at predictive models. So it's really exciting to see the students take this on, because I have an ongoing contract with HRI where we call it the e-predictor. We actually have some models that we've been working on. I say we're about to start year 3 on it, and it's been quite a process for us when it comes to the number of models that were used, when it comes to predictability, and when it comes to working with the local jurisdictions on who's going to want us to publish the model for their sites, right? Because at the end of the day, when it comes to the GLO and how we provide this information, we have to think about how it's going to affect the local communities to have a predictive model, how it's going to affect the money that's coming in for the weekend, right? So for us, when it comes to a predictive model, I'm looking at a predictive model that can give me up to 3-day turnaround, maybe even a 7, but nothing more than that. And the reason being is because people do change where it is that they want to go visit for the weekend. And we have to take into account that depending on what we put out there, it could affect where they're going to go spend their money for the summer, for the winter time, when it's still warm in Texas. So I can tell you right now, the city of Corpus, the city of Galveston, they're excited about the fact that we're going to have a predictive model. Right now, our models are running anywhere from 80 to 95% accuracy. But we started off with 50 models as well. The other thing is the smaller towns are like, absolutely not. We do not want you to do that. So then when it comes to us and when it comes to what our databases look like on the backside, we have to start to plan, okay, what kind of changes do we need to make to our website? What kind of changes do we need to make in our infrastructure when it comes to holding this data to be able to turn on and off a model for the public? And how are we going to present that? So when it comes to students working on these models, we get excited because we're like, maybe they're seeing something that we never even looked at. And how can that help us to improve what we've already been working on for the last 3 years? So it's exciting to me when I see students that I saw that you guys did more than 50 models. And when you showed me what you were using and which parameters you were using for your models, that's exciting to me just because those are some things we didn't use in our models. So even I'm learning as I see your final results.
Thank you, Lucy. Sounds great. Thank you very much. John, did you want to add anything? We want to forget about you? Okay.
Nothing else to add. Thank you.
Thank you. Thank you very much. Anybody else online or here?